Good evening. Good evening, everyone.
Sir, your voice is not audible. Sir, please check mine.
My voice is not audible.
Yes.
Now, sir.
I can hear you.
Hello, Dhruti sir, am I audible?
Yeah, I can hear you. Can you hear me?
Yes, sir, very much, very clear.
Okay, great.
Okay. Good evening to all the dear participants. So let us begin today's session. Today we have two eminent personalities with us. To begin with, the first session will be from Dr. Dhruti Ghosh sir, presently Associate Professor, Department of Physics, Indian Institute of Technology, Dharwad. And it would be my immense pleasure to introduce before you all today's resource person. Dr. Dhruti Ghosh graduated from Dibrugarh University, Assam in the year 2003, did his Masters in Physics from Indian Institute of Technology, IIT Guwahati, India in the year 2006, and PhD in Photonics from the Institute of Photonic Sciences, ICFO, Barcelona and Spain in the year 2012. He is a recipient of Ramanujan Fellow from National Physical Laboratory, New Delhi, and BDP Research Fellow from Dresden Integrated Center for Applied Physics and Photonic Materials, Dresden, Germany, and he did his postdoctoral research from Institute of Photonic Sciences, Barcelona, Spain. To his credit, he has several awards and recognitions. Best Poster Award in the year 2017 in Photomask Technology and UV Lithography. He is a recipient of Best PhD Thesis Award in the year 2012 from the Institute of Photonic Sciences. Student Innovation Award in the year 2011, and this particular award it will be the Pan-European Award given to promote research in photonics related to R&D with industrial impact and is awarded annually to a person whose age is less than 35, and Best Poster Award at ICFO Annual Poster Session event on Corporate License Day, Barcelona. He is a recipient or fellowship of from Catalonia government to carry out postdoctoral research at Dresden Integrated Center for Applied Physics and Photonic Materials, Germany. FPI Fellowship from Ministry of Science and Innovation, Spain, to carry out doctoral research at ICFO. He has several recognitions to his credit. PhD thesis, his PhD thesis was chosen for Spinger Thesis Series. Internationally top-ranked research institutes select their best thesis annually for publication in this series. Nominated and endorsed by two recognized specialists, each thesis is chosen for its scientific excellence and their impact on research. And congratulations, sir. And he is represented ICFO in 5th India-Spain Dialogue held at Madrid, Spain. To his credit, he has 6 patents, published more than 60 articles in refereed journals, and is represented 10 plus invited talks, and has as on now he has 5 books chapters. With these brief words, I now present before you today's resource person, Dr. Dhruti Ghosh. Over to you, sir, and thank you very much for accepting your invitation as a resource person for this ATAL FDP. Over to you, sir. I hope.
Thank you. Yeah. So first of all, thank you, Dr. Samir, for inviting me, giving me the opportunity to talk. And it was not a brief introduction; it was quite a long introduction. So anyway, thank you. So without any delay, maybe I can start the presentation. So I will start by sharing the screen. Let me know if I am doing it correctly.
Well, sir.
So is it
Yeah.
visible?
Yes, it is visible. Now it is visible, sir, clearly.
Okay, okay, great.
Thank
Okay, so good evening to all of you who are present here. So in this FDP series, I'm going to present a talk on perovskites, the future of photovoltaics. This is the topic title of my talk today. I am an associate professor in the Department of Physics at IIT Harvard. Let me go to my pointer options. Yeah, okay. And I lead the group, which is a thin film photovoltaics group here in IIT Harvard. So, so first of all, I just would like to give you a brief idea about why we chose this particular topic and why we need to work on this particular topic, which is about photovoltaics. So as we all know, that we need energy. Energy, if you look around us, that everywhere we need energy. Energy for lighting, energy for running electronics, energy for moving from one place to another. So we need electricity. And we need energy in general. And electricity is the main form of energy which is currently available to us. If you take a look carefully, the picture which I have shown to you, this is a graph which I got it from the United Nations website, and it talks about on the y-axis it has Human Development Index, and in the and the y-axis and the x-axis it is annual per capita electricity use, and it shows different countries. And if you take a look around, so India is somewhere around here, and all the green countries, the countries which are represented by green dots, they are mostly the industrialized countries. Okay, they are, or in other words, you can say that they are, the most developed nations. So as the x-axis is about annual per capita electricity use, which means the more you towards the right hand side, these countries use more electricity. Okay, Canada, US, Australia, Japan, these are the countries which use the most of the electricity. On the y-axis, it is the Human Development Index. So the more you towards the top side, it is better in terms of the Human Development Index. How happy the people are, what is the average age, these are the criteria which have been chosen to calculate this Human Development Index. So we want to be on the top side as well as on the right hand side. And if you can see that, all the nations which have the high Human Development Index, they're on the top side, on the right hand side. So you can see UK, Netherlands, Japan, Australia, US, and Canada. Okay, so from this graph, we can conclude that the nations or the countries which are using more electricity, they are more happier compared to the nations which use electricity less. So we would like the India to go from here, from this position to this position, to be more happier, right? And this is only possible if we use more electricity. Well, it doesn't mean that we waste our electricity. It simply means that we have to use the electricity for industrial development, for opening up new industries and all those things. Okay. Now we understood that we need more energy to be more happy as a country, right? So just take a look at this particular figure. This is a figure which shows the amount of energy which is available currently in the Earth's crust. So this brown dot here is the annual usage of electricity or the energy which is required for the whole Earth. Okay, and on the circles or the spheres which is on the right hand side is the amount of energy which is available in the form of different sources like uranium. This is a uranium. This is for petroleum. This is natural gas, and this is wind. Okay, and this is at taken at all together. Whereas the yellow circle, which I can see here, this is the is the amount of solar energy which is available to us only per year. Okay, so our requirement is this brown circle, but the amount of energy which we receive on our Earth from the sun is this yellow circle. Okay. In addition to this, you can also see some other sources of energy like biomass, hydro, geothermal, and tides as well. But just a quick look at this graph suggests you that solar energy which is we receive at the Earth is absolutely more than sufficient to meet all the energy requirement of the Earth. Okay, so with this motivation, I will move forward. So this is typically whenever we talk about photovoltaics, generally people has a confusion or some doubts in their, in their mind that whether solar cells or photovoltaics, is it good enough to give us the electricity? So if you have that confusion, this figure will clear out that confusion. Now, this is the world graph or the world map, as you can see, and the color codes are representing here the amount of solar energy which is being falling on the Earth crust. As you can see, the regions which is towards the red in color receive the more solar energy compared to the regions which is shown in blue color. And the black dots which I can see here represents the area of the Earth crust which needs to be covered in solar cells, with solar cells having an efficiency of only 8%. Okay, so if we cover the Earth of these areas, these black dot areas, with a solar cell which is having an area of efficiency of 8%, it is enough to to meet all our energy requirements. So it doesn't mean that if you want to use solar cell for everything, it doesn't mean that we have to cover everything with the solar cells. Only this much dot area is enough to produce enough electricity for the whole electricity required by the humankind. And it has to be noted here that I guess somebody, I'm sorry, but somebody's mic is on. Can we switch off that mic?
Yeah, yes, sir. I request. Somebody's participant's mic is on. Please switch off the mic, please. Dear participants, somebody's mic is on. Please turn it off. Yes, sir. You may continue, sir, please.
Okay, great. Thank you. So it has to be noted here that I say that this solar cell which needs to be covered, these black dots, they have efficiency of 8%. Please note that the commercially available silicon solar cell which is available in the market, they have an efficiency of 18% or 18 to 20%. So in actual, we need to cover even smaller area as shown in this picture. Okay, so as far as their feasibility is concerned, solar cells are good enough to meet the energy requirements of the humankind. Okay, with this motivation, let's move ahead. Now I will talk more about photovoltaics. What are photovoltaics? How they come into the picture. Okay, so let's first define what do we understand by photovoltaics. Okay, so this is the branch of technology we concerned with the production of electric current using the material that exhibit photovoltaic effect. Now, question is, what is photovoltaic effect? Photovoltaic effect is nothing but when the sunlight or the light is converted to electricity. Okay, so photovoltaic effect, it is a creation of voltage and current in a material when it is exposed to light. Now the question is, what kind of material we are talking about? Is it insulators, is it metals, or it is semiconductor? Which kind of material should we use for making such a photovoltaic cells? So well, before we understand which kind of material which should be used, let's see what is a solar. So this is just a schematic. So this is a solar cell, light comes in and it produces electricity. Okay, and this is the solar spectrum, or the light which comes in onto the Earth's crust. As you can see, the light is mainly concentrated in the visible part of the spectrum, which is most around 60% of the light which or the photons which reach the Earth's crust. We do have also some IR part and the UV part, but most of it is filtered out in the atmosphere. So if you are making a solar cell, we should concentrate on utilizing this part of the solar cell. Okay, so if you can, because this is the most intense part of the solar cell spectrum which is reaching the Earth's crust. Okay, with this in mind, let's go back to the original question. What should we use? Should we use insulators? Should we use metals? Or should we use semiconductors? Well, imagine if a metal, in the case of metal, the valence band and the conduction band, they overlap with each other. So if light comes in or photon comes in, what happens is that, as we already know, the light is reflected back. Light comes in, it is reflected back, right? Most of the metals, they are good reflectors of light. Okay, they do not absorb the light. What happens in the case of insulators? In the case of insulator, the conduction band and the valence band, they are separated by a large band gap. Okay, very large band gap, typically above 3 electron volt. In such cases, even if photons comes in, what happens is that those photons are not absorbed. Okay, so they comes in and they pass away. So they are not utilized by the material. However, in the case of semiconductors, their band gaps are typically in the range of 0.7 volt to 0.7 electron volt to around 2 electron volt, and this band gap is syncs with the incoming photons which in the visible part of the spectrum, which means if light comes in and falls on a semiconductor, the chances of getting absorbed by this material, which is a semiconductor, are very high. Okay, metals cannot absorb, insulators cannot absorb, but it's the semiconductors which can absorb the incoming light. Okay, so which means that we need to use this particular type of material for making a solar cell. Okay, now typically whenever we talk about photovoltaic cell, people get confusion with photoelectric effect. So I just wanted to make sure that we all understand that how photoelectric effect and photovoltaic effect are different. Now, if you recall from your class 12th, this is the first time when we read about photovoltaic effect, photoelectric effect. In photoelectric effect, light comes in and the electrons are ejected from the surface of the material. Okay, the electrons which are on the top surface on the surface of the material is get ejected out. Okay, here also electrons are produced, but the electrons comes out from the surface. Okay, and not all light can make this happen. Only some wavelength of light or some energies of light whose value is more than the work function of this particular material is able to extract the electrons. Whereas in the case of solar cell or photovoltaic cell, what I will do is that I will first show you how solar cell schematics looks like. So in the solar cell, we have a material. We already know that particular material, we call it active layer, and this is a semiconductor layer. Okay, remember in the photoelectric effect, it happens mainly in the case of metals, whereas the solar cell or the photovoltaic cells, they are made up of semiconductors. So we have a material which we call it as an active layer. This is a semiconductor layer. When light comes in, light is being absorbed. I already told you that light can be absorbed by the semiconductor layer, semiconductor material. So light is being absorbed. When light is absorbed, electrons and holes are produced. Okay, how they are produced, I will tell you later on. But for the time being, let's assume that when light comes in, light is being absorbed by the material, which is a semiconductor layer, which we already also call as active layer, is absorbed and it produces electrons and holes. Once these electrons and holes are produced, we need to collect these electrons and holes. Once we put one electrode on the top, one electron on the bottom, and one electron on the top, these, let's say for example, holes is collected by the electrode number 1, and the electrons, which is shown by the negative sign, if they're collected by the electrode, then the electricity is produced. And what do we see? It seems that the major difference between the photoelectric effect and the photovoltaic effect is the fact that the photoelectric effect happens on the surface level, whereas the photovoltaic effect happens in the bulk level. Means light is being absorbed by the material itself. It's not only happens on the surface, but it also happens in the inside the material. It's a bulk effect. Okay, and here electricity is produced. Okay, with this, and of course there is a substrate onto which the solar cell is prepared. Okay, so this photovoltaic effect was first discovered in 1839 by this French scientist, which is Alexander Edmond Becquerel. What he discovered is that when he claimed that the shining light on an electrode submerged in a conductive solution would create electric current. So this is in 1839. As you can see here, he dipped 2 electrodes, platinum electrodes, as you can see, and he dipped it inside a inside a conductive solution, which is basically an electrolyte. Okay, and when light comes in, what he saw is that a current is generated between these 2 electrodes. Okay, and this is in 1839, and this is the paper which he published in 1839, showing that the photovoltaic effect exists. Okay, many of you might know that his surname Becquerel. If you remember, this surname is very famous actually. Becquerel. His father was Anton Becquerel, who was again a very famous scientist who studied luminescent, and his son is Henry Becquerel, who shared the Nobel Prize with Marie Curie for the discovery of radioactivity. So his whole family is consists of great scientists. His father was a great scientist. He himself was a great scientist, and his son also was a great scientist. Okay, great. So let's see the timeline of photovoltaics. Okay, so we already seen that in 1839 the photovoltaic effect was discovered. and it was discovered by Edmund Becquerel. And so it was in 1839. Then in 1873, 76, selenium. Scientists proposed that selenium, which is again a semiconductor, is better material for making solar cells. Okay, and they made solar cells out of this particular material in 1873 to 1876. We're using this selenium as a material. Then in 1883, first solar cell was created. Okay, with this particular selenium. Okay, selenium as a active layer, and the electrodes were consist of gold. But the active layer, what do we understand with the active layer? Active layer is the semiconducting layer which actually absorbs the incoming sunlight and converts those incoming photons to electrons and holes. Okay, and the gold is there to collect the electrons and holes. Okay, to complete the circuit itself. Okay, and the efficiency of that first solar cell was somewhere around 1 to 2%. Okay, please note that the most of the modern solar cells which you can find from the market is consist of around 18 to even 22%. Okay, and then in 1887, sorry, photoelectric effect was observed, which is quite similar to photovoltaic effect. Then in 1953, silicon solar cell produced commercially. So people have moved on from selenium and they have moved to silicon. And these three famous scientists, Pearson, Chapin, and Fuller from Bell Laboratories. Bell Laboratories, they produced the first silicon solar cell, which was around 6% efficient. So as you can see, the first 1883, the efficiency was 1 to 2%. But in 1953, almost 60 years, it took humankind to increase the efficiency from around 1 to 2% to 6% efficiency. Okay, and in 1956, this was a company which was Western Electric, which started selling commercial solar cell for public use. As you can see here, this is an advertisement for the silicon solar cell. Somebody has put up the solar cell in the garden. As you can see here, this is the batteries to store the energy. These are the famous scientists, three famous scientists who made the solar cell out of the silicon in the Bell Laboratories. And this is the paper, which was in 1954 when they produced a silicon solar cell, which was around 6% efficiency. Okay. Okay. So, and once the solar cell have came up in 1956, the first commercial use of solar cell happened in 1958. So it is the first time, when the satellite Vanguard was launched in the space in 1958. Okay, so this was because we all understand that we need energy for satellites. Also, they need energy, and what is the source of energy for them in the space? It is the solar cells. So these silicon solar cells was first used in Vanguard 1. This is the satellite, used by the Soviet Union at that time, and till 1968. The communication was lost with this satellite, but it has traveled more than 97,000 kilometers revolutions around the Earth in 50 years, and it is still there in the Earth orbit. Okay, so this satellite was around 1.47 kilos and the diameter of 16 centimeters, and as you can see, it has some solar cells in it because it needs energy. So people at that time were not so much convinced of the solar cell, that whether they can be used for real purpose. But as you can see, at least by 1958, some scientists have realized that we need them at least for the satellite uses. Okay, maybe not for the household, but at least for the satellite uses, it can be used. Okay, so let's moving on. So this is an efficiency chart. Okay, don't get confused. I will try to explain everything here. So this is an efficiency chart which is maintained by NREL. This is National Renewable Energy Laboratory from Colorado in US, United States of America, which plots this curve for cell efficiency against the year. Okay, as you can see, it is year. So silicon solar cell, they came up in 1956. So these blue colored cells represents the silicon solar cells. Okay, and as you can see, the silicon solar cells in 1956 it was around 6%. And around 1975, it is around 11%. It has improved, and now somewhere around here, its efficiency is around 27.8. As you can see here, 27.8 silicon solar cells. So we have improved, but we have improved from around 1 to 2% in 1883 to around 27.6% in latest research. Okay. There are other technologies as well which has higher efficiency. As you can see, these purple color lines, they have higher efficiency. For example, this one represents type 234 junction concentrator solar cells. They have an efficiency around 47%, and and these are the solar cells which are currently being used in the in satellites. We do not use this type of solar cell in our household because they are very, very costly. We use the solar cell which you see in the street lights or in some homes or houses or in some particular buildings. They are mainly silicon solar cells, but these are the solar cells which are very costly. They are mainly used in the case of satellites, because for the satellites you don't care about the cost, you only care about the efficiency. But here, one thing which I want to show here, there are some other technologies which has came up recently. Okay, so silicon came up in 1883, but these are the solar cells which came up very recently, as you can see here, and their efficiency has also rose very rapidly. I will try to zoom in here, as you can see here. So these are the new technologies which has come up. These are the emerging photovoltaics. Okay, dye-sensitized, perovskite solar cells, organic solar cells. There are many types of solar cells. What I want to highlight here is that these solar cells, the one with the yellow colored ones. Okay, so what these yellow colored ones are perovskite solar cells. So the first perovskite solar cell came up in 2009. Okay, 2009, which is not very far away from. We are in 2025 right now, so it's around around 14 or 15 years ago. So the first perovskite solar cell came in 2009, and now its efficiency around 27%. Now, it's important to note here that silicon solar cell took 100 years to reach from 1 to 2% to 27%. But this perovskite solar cell took around 15 years to reach an efficiency from around, in 2009 its efficiency was around 3.4%. Right now the efficiency is around 27%. So in a very short span of time, this particular solar cell, particular type of solar cell, which we call it as a perovskite solar cell, have reached efficiencies which is comparable to that of the silicon solar cell. I have even more clearer picture here. As you can see here, this is the perovskite solar cell here. It came up in 2009 actually, and right now it is around 27%. And silicon solar cell is this one, the blue colored one. Okay, and you can see this blue one and the yellow one, they are very close to each other, which means the efficiency which we are getting with the perovskite solar cell is similar to that of the silicon solar cell. What I want to focus you all here is this one. This one. As you can see here, this is efficiency is close to 34%. And what is it? This is hybrid tandem, which is a combination of perovskite and silicon. So this is something which is combine the technologies of silicon and perovskite. When you combine these two technologies, you can make solar cells which are even more efficient, which is around close to 34%. Okay. Now, we have seen that we have talked about the efficiency of solar cells. So which means, what do we mean by efficiency? Efficiency is nothing much. Suppose you are getting 100 photons from the sun. From the 100 photons, how many electrons I'm able to generate? Okay, this is the efficiency. How much electricity I'm able to produce from the solar energy which you are getting. Okay, this is your efficiency. So the efficiency, the efficiency depends on many factors, many things. It is nothing but it is the multiplication of efficiency of how much light is being absorbed. If my solar cell is not able to absorb all the light, I will not be able to get more electricity, right? More light I absorb, more better is for my efficiency. Okay. And charge excitation. When light is absorbed, electron holes are pairs are produced. So how much the charges are being excited? This also depends. Then diffusion and drift. How much charges are separated and how much charges are collected. So, the efficiency of a solar cell depends on many parameters. I do not have time to explain everything, but I hope that by the time this talk ends, and if you've listened to it carefully, you will have the basic idea about what is a solar cell and how does it work, what is a silicon solar cell and what is a perovskite solar cell, how these two technologies are different, and how these different parameters like absorption, excitation happens in a solar cell. Okay, great. So let's move forward. So we already know that we need semiconductors, right? Without semiconductors, we cannot have solar cells. Why semiconductors? Because metals, if light falls on metals, it will reflect them. And if light falls on insulators, light will pass through it. It will not absorb it. So we need semiconductors to absorb the light. This is the first criteria for solar cell, that I should be able to absorb the light. Once I absorb, then I will see whether I can convert that absorbed energy, absorbed photons to electricity or not. That's a different step. But the first step is that I should be able to absorb the light. So this is a semiconductor. Okay. This is the edge of the conduction band. This is the edge of the valence band. This is the Fermi energy. Okay. So light comes in. Light consists of many wavelengths. So I have shown in the red, green, and blue. This is the spectrum. Light comes in. Some of the light is being absorbed by the semiconductor depending upon the band gap. How much light is absorbed, it depends upon the band gap. So some of the light will be absorbed. Maybe some of the light will pass through it. Once light is being absorbed, electrons, holes are produced. Okay. So when light comes in, it is absorbed, electrons and holes are produced. Electrons are produced in the valence conduction band and holes are produced in the conduction band. Okay. Now, what happens if I join a p-type semiconductor and an n-type semiconductor? Okay. So I guess that you already know what is a p-n junction diode. What is a diode? This is something which we have covered in our class 12th. So if you join a n-type semiconductor and a p-type semiconductor, the band level looks like this. Okay, and this continuous line here is the some people call it Fermi energy, some people call it chemical potential. Whatever name you feels good, it's fine. But this is nothing but your Fermi level. And when you join this n-type semiconductor and p-type semiconductor, and without any biasing, without any external battery, this Fermi level aligns itself. Okay, this is something which we know from our class 12. So what happens when we have a p-n junction diode and light falls on it? Of course, this is the depletion region. If you remember, this is the region between the n-type and p-type material. This the sandwich region is known as the depletion region, and the direction of the field, because a field is produced when we join n-type material and p-type material, and the direction of that particular field, this electric field, is from n to p-type. Okay. Okay. So junction is produced, and what happens when light falls in? Suppose light falls in. I'm assuming that light is coming from this side, and when light is being absorbed by these two materials, n-type material and p-type material, what they produce is that they produce holes on the valence band and electrons on the conduction band. Okay, photons comes in, and an electron is excited from the from the valence band to the conduction band. So the red lines here, red dots here are the electrons, where the blue dots are here, the holes. Okay, positively charged. This is negatively charged. Similarly, the same case here in the p-type as well. So light comes in, electron hole pairs are produced. So these are the electron hole pairs. These are electrons, these are holes, these are electrons, and these are holes. Okay. Now look at this particular region, the junction, the depletion region. So there is a slope here. Okay, there is a slope here. So when these electrons when these holes feels this field, they try to move. In which direction they will move? The electron will move from this side to this side, whereas the holes will move from here to here. Why they are moving? What is the reason for they are moving? Because there is a field here, right? There is a field here. If I take only n-type, if I take only p-type, and if I try to make a solar cell out of only n-type or only p-type, then this movement of charges will not happen. Because to make a solar cell, I need the movement of charges. Making them is fine. So whenever light comes in, they are excited, they make electrons and holes. But we need to move that, because electricity is nothing but the movement of charges, right? So electrons move from here to here, where the holes move from here to here. You can assume electrons to be like a heavy stone, which always wants to go down, whereas the holes are like hot air balloons, which always wants to go up. So as you can see here, the holes are here. It wants to go up. It feels the field, and when it feels the field, it goes from here to here. Similarly, the electrons feels the field. Which field? This junction field, the depletion region. And when they feel the field, they move from here to here. So which means the charges are moving, and whenever charges moves, it makes electricity, right? So once this, then what I do is that when I put one electrode here and one electrode here, and the electrons fall from here to here, they will move here, and the holes move from here to here. And when they're connected, it makes the whole circuit, and thus the electricity is produced. Okay. Okay. Now, whatever I've told you, I will. This was a schematic, and I will try to explain it in more, elaborate way. Okay. So this is so it's very clear that we need PN junction diode for making a solar cell. Okay. Why PN junction diode? I already explained, because we need movement of charges. If we don't need movement of charges, only p-type material and only n-type material was enough to make a solar cell. But we need, movement of charges. That's why we need PN junction diode. So as you can see here, so this is a p-type material, this is an n-type material, and this is a diode in dark. When I put the PN junction diode in dark, there is no current there. What will happen? So, and there is no biasing. So as you can see, no bias, forward bias, reverse bias. Okay, and we will try to understand this phenomena in 3 different cases, 3 different way. This is the schematic, this is the band level diagram, and this is the current voltage curve. Okay, how in 3 different ways. So okay, so when there is no biasing means there is no batteries connected to this PN junction diode, and there is no light. So this is a p-type material, this is an n-type material, the Fermi level is aligned. This is the same figure which I have shown in the previous slide, and when you join a p-type material with an n-type material, what will happen? Electron diffusion takes place and electron drift takes place. I hope you already know what is a diffusion and what is a drift. Diffusion is a movement of charged species under the influence of concentration, whereas drift is the movement of charges because of the field. Okay, so when at the equilibrium position, the diffusion current and the drift current both are equal. As you can see, the length of the arrow which I have put in here, diffusion and the drift, they are of the equal size, which means the diffusion current and the drift current are of equal size, and they are of opposite in nature. Okay, that because what is diffusion actually? So we have n-type material on the right hand side and the p-type material on the left hand side. So when I join an n-type material with the p-type material, the electrons, n-type is what? N-type means they have more electrons, right? So when there are more electrons, the electrons will try to move from this side to this side, right? So as you can see, the electron diffusion is this one. Whereas drift is what? Because there is a field here in the depletion region. The electrons which are here in the p-type, the minority charge carriers in the p-type, they will try to move from here to here. And the drift and the diffusion, they are opposite to each other. At some point of time, then equilibrium will be reached, and the both of the current will be of equal size and opposite in nature. That's why you get an IV curve, you will get zero current. So this red cross which you see here is the zero current. Okay. Now, what will happen if I forward bias this particular PN junction diode? Okay. So what I did is that I connected the P side to the positive terminal and N side to the negative terminal. Okay. So when you forward bias a PN junction diode, what will happen? This barrier junction reduces. We already know from our class 12. This barrier junction reduces. Okay. As you see, this is this much height and this is small height. So barrier junction reduces. Okay. If this happens, what will happen is that the electrons which wants to move from this side to this side, from N side to P side, they see is less barrier, because from moving from here to here, they see this much of barrier. But in this particular case, they see a small barrier. So which means the diffusion will increase, whereas the drift will decrease. Why drift is decreasing? Because my depletion region has decreased. Okay. So diffusion will increase, whereas the drift will decrease. As you can see, the diffusion is more, and the current direction is from the right to left. So this current is more. So the more the current was zero in the first case, but now we will have a positive current. As you can see here, the cross has moved from zero position to this position. So a current is produced in the circuit. Okay. Now what happens in the case of reverse biasing? In the reverse biasing, you connect the opposite way. Your P side is connected to the negative terminal, whereas the N side is connected to the positive terminal. Okay. And what happens in the case of reverse bias? This depletion region decreases. Here the depletion region decreases. In here the depletion region, increases. In this case, it increases, as you can see. If I compare this one with this one, as you can see, it is increased. Okay. Now the electrons which want to move from here to here, the majority charge carriers, they see even more height, so they cannot move, which means the diffusion current will reduce. Whereas the drift current is because of the field, remember. So drift current, so the minority charge carriers, which are electrons here, they will feel easier to move from p side to n side. So the drift current increases. But since my current direction is from right to left, this will be negative current. Okay, as you can see, this is negative current. Okay, so this IV curve is nothing but the IV characteristics of a PN junction diode. As you can see, this is the junction diode which we already know from our class 12. So this is the IV characteristics of a junction diode. Simple. So when there is no biasing, this is the point. When there is a forward biasing, we get in the first quadrant. When it is reverse biasing, we get current in the third quadrant. Okay. Now, whatever I have explained till now, this was diode in dark. What happens if I do the same experiment? Everything remains the same, but now in the presence of photons, in the presence of sunlight, okay, or in the presence of light, what will happen? Now, the condition is that diode under illumination. Okay, now light is there. Everything else remains the same. Only thing is that because this is a PN junction diode and this is a solar cell, one more current will appear. One more current. Earlier it was only diffusion current and drift current. Now one more current, which is, we call it as illumination current, ILL, illumination current. Okay. So when light falls in, electrons will move here, holes will be created here. Electrons will be created here, holes will be created here. And when there is no biasing, as you can see, diffusion and drift, they are canceling each other. But the electrons which are produced here and the holes which are here, holes will move from here to here, and the electrons will move from here to here, as I have shown in the previous animation. So there will be a large illumination current which is from left to right, and this is the reason why I have drawn a larger length arrow here showing the illumination current. And this current is negative, because I said my current direction, my positive current direction is from right to left. Okay, right to left, but this illumination current is from left to right. So this is the current is produced, but this current is negative current. And that's the reason why for zero voltage, because there is no biasing. So for zero voltage, I get a current. And this current is because of the photons. It's not because of the diffusion. It's not because of the drift. It's because of the photonic. This is because of the illumination. Now, what happens in the case of forward bias? We already know that what happens in the forward bias. In the previous slide, I've shown it to you that the depletion region decreases, right? And the diffusion current increases, whereas the drift current decreases. But the illumination current remains the same, okay, because it is continuously illuminated. So now we have to take the vector sum of these three arrows. What you will get? You will get slightly less current, okay? Slightly less current, but overall, it's a negative current. So it is a negative current. It is less than this one, but it still is a current, but it's a negative current. And since we have a forward biased it, the voltage is positive. Voltage is positive here, okay? But the current is still negative. Now let's move to the reverse bias, okay? So reverse bias, again, we already know the diffusion current is less, drift current is slightly larger, and illumination current remains the same. So we have to take the vector sum of these three. What you will get is that a more current still, but is in the third quadrant, because now the voltage is also negative. In this case, the voltage was 0. In this case, the voltage was positive. Forward bias means positive voltage. Reverse bias means a negative voltage. So voltage is negative. Current remains the same. More or less the same amount here as here. As you can see, this is the game. So if you join these three cross, you will get something, a shape like this. So this IV characteristics, this IV curve is exactly the same as this case. Only thing is that when it is dark, only thing is that this IV curve has shifted downwards, as you can see. Okay, as you can see, right? IV curve, the shape remains the same. The only thing is that when it is dark, it is following this pattern. When it is under illumination, current is being produced. Okay, an extra current is being produced. Okay, I hope that you have understood it. So let's move forward. So this was the IV characteristic of a solar cell or PN junction diode when there is no current. When there is current, the IV curve shifts towards the fourth quadrant. Okay, and the IV curve, where it touches the voltage axis, we call it as the open circuit voltage, and the axis and the current axis where it touches, we call it as a short circuit current. Okay, and the question is, how do we define efficiency in terms of electrical parameters? Okay, we already understand the physical meaning of efficiency. How much efficiency means how much I'm able to convert the incoming photons to electricity. But in terms of electrical parameters, we define efficiency as we know for any other devices, input power by output power. Okay, so output power is nothing but multiplication of this VOC, JSC is nothing but this particular point, and the field factor divided by P input. What is P input? P input is the incoming solar sunlight, okay, which is typically 100 watt per meter square. Okay. Now you must be thinking about what is FF, what is field factor. So we define this field factor. It's nothing but the ratio of these two rectangles, S1 by S2. What is S1? What is S2? Let's say first, S2 is nothing but the multiplication of VOC and ISC. Okay, so this rectangle. What is the area of rectangle? Is nothing but the VOC multiplied by ISC. Whereas what is S1? S1 is the point. This particular point is this is the point where we have the maximum power. Okay, which means along this particular curve, at this particular point, the multiplication of voltage versus current has the maximum value. So we call this particular point as the maximum power point. Okay, and we define this field factor at this particular point. Okay, you take the ratios of these two rectangles. This is how field factor is defined. Okay, and electrically, from the electrical engineering point of view, a solar cell is nothing but a PN junction diode connected in parallel with a current source. Okay, you might have imagined it already that a solar cell is nothing but a constant current source, but since it is a PN junction diode, so they are in parallel combination. Okay, this is an ideal scenario. Of course, there will be much more resistances. There are some series resistance will be there, some shunt resistance will be there, but this is an ideal scenario. Okay, when we have a current source in parallel with a PN junction diode. Okay. Okay. Now we have understood what is a solar cell, why we need a semiconductor. Now I will try to go a little bit deeper into, and I will try to define excitons. Okay. Why do we need to understand exciton? This is a little bit of deeper physics which we need to understand. Okay. If you remember, when I was showing you, this diagram, or even the diagram before this one. Yeah. You see, when light comes in, it produces electrons and holes, right? Electrons on the conduction band and holes in the valence band. So whenever one photon is being absorbed, one electron will be excited from valence band. It will go from here to the conduction band. This pair of electron and hole, we call it exciton. Okay. So let's go back to my diagram. So this is the exciton. So an exciton is a bound state of electron, and sorry, this is some mistake. So it's a bound state of electron and hole. It should be only hole. Electron and hole bound state is known as exciton. Okay. So this is a hole, this is an electron. They are bound to each other. Okay. They are separated, but not exactly separated, whereas they are still bound to each other. Now the question is why we need to understand this concept of this exciton. Why do we need in the case of solar cells? Now if you remember from your class 12, from the Coulomb's law, what was the Coulomb's law? Coulomb's law was that if there are two charges Q1 and Q2, the force between those two charges is nothing but 1/4 pi epsilon naught Q1 Q2 divided by R square. Okay, this is in the case of vacuum. If those charges Q1 and Q2 are in the vacuum, what happens if the charges are not in vacuum but some other medium? So let's say, for example, a medium which has dielectric constant of epsilon R. I hope you understood. This is epsilon R. This epsilon R is coming because this is not in vacuum but is for some other medium. Okay. Now value of this epsilon R in the case of organics is around less than 4. For silicon it is around 11 to 12, and for perovskite material it is around of the same order of 10 to 18 value number. Okay, which means that when an electron and hole is created in a organic solar cell, or say in an organic material, okay, because the value of epsilon r is small and this epsilon r comes in the denominator, the force will be larger. Okay, they're inversely proportional to the epsilon r, which means in the case of organics, when an electron and hole pair is created, they will be more bound to each other. Okay, they will be more bound to each other because the force will be higher. Whereas in the case of silicon or perovskite, because they have a larger values of epsilon r, this force will be less, which also means that this electron and hole which is being produced, they will be, as soon as they are produced, they are easy to separate because the force of attraction between this positive and this negative is less because they have higher epsilon values, which also means that if you make a solar cell out of organic material, it will have less efficiency because they are not easy to separate, the positive and the electrons. Okay, the electrons and the holes. But in the case of silicon and perovskites, because the epsilon value is higher, they're easy to separate. If they're easy to separate, they will move in the opposite direction. If they are moving in the opposite direction, they will constitute the current in the external circuit. Okay. Okay. Now, how does a silicon solar cell looks like? Remember this topic, this talk is about perovskite solar cell, but still without understanding silicon solar cell, it is difficult to understand silicon solar cell. So I just put a typical picture of a silicon solar cell. As you can see here, a silicon solar cell consists of a base and emitter. Base is nothing but p-type material, emitter is nothing but n-type material. So this is p and n, so it's a p-n junction diode. As you can see, light comes from the top, electron holes are created. Some electrons are collected here, holes are collected here, and this how and these fingers, as you can see, they are the electrodes here. Okay, so this is how typical silicon solar cell looks like. Now we will move to perovskite solar cells. Okay, before I actually show you the device architecture of a perovskite solar cell, we need to understand what is perovskite material. Silicon, we already know silicon, Si. We already know this atomic number. What we already know is atomic configuration. From class 6 onwards, we know about silicon. Silicon is a backbone of electronic industry. We all know. But what is perovskite material? So perovskite is a material which has the chemical formula of AbX3. Okay, AbX3. So A is in the middle, B is in this black ones, and this X is the purple ones. This is the structural crystal structure of a perovskite material. What is A and B and X? A is typically larger cation, which is typically can be organic, like this is methylammonium, this is formidinium, this is ammonia. This can be inorganic as well, like cesium. B is typically lead, and X is typically halide. Okay, so these three type of materials, when they combine in this particular crystal structure, they make perovskites. Okay, and they have a formula of AbX3. Okay, X is typically halide, B is typically lead, and A, as you can see, the blue one here, is typically could be organic, like this one, or this one, or this one, or it could be inorganic, like cesium, CS. Okay, now I've also defined something which is known as Goldsmith tolerance factor, which is defined as T equals to radius of A, radius of X, divided by √2 multiplied by this formula. So when the value of this T becomes close to 1, we say that this crystal structure is stable. Okay, if you want to make a stable perovskite, the value of this should be close to 1. Okay, so this is about the chemical composition and the crystal structure of perovskite solar cell. Now I have already shown this picture to you previously to show you how a solar cell looks like, and or a schematic of a solar cell. So schematic of a solar cell consists of an active layer. In this case, it's a perovskite. Light comes from the top, and we have two electrodes on the top, one on the top and one on the bottom, and we have substrate onto which the solar cell is made. Now, in the case of perovskite solar cell, the schematic is not so simple. It consists of, two more layers. So what are those two layers? So these layers are known as transport layers. Okay, transport layer 1, I call it transport layer 1 and transport layer 2. Okay, now the question is, why do we need extra layers here in the case of perovskite solar cell? Why not only the two electrodes and the active layer? Isn't it enough? Why do we need to make it more complicated? Say transport layer 1 and transport layer 2. We will try to understand that. Okay, Okay, so imagine this is my perovskite layer. Okay, so light comes in, what will happen? Electron and hole will be created, right? These are holes and these are electrons. Remember, in the case of PN junction diode, once these electrons and holes are produced, they moved in the opposite direction, right? They moved in the opposite direction. But in the case of perovskite solar cell, and why they moved in the previous case, in the case of PN junction diode? Because it sees an electric field. When I joined the P-type material and N-type material, when it joined, it formed the electric field there. But there is no electric field here, right? There is no electric field. So the charges which produce in the perovskite material, they will not move. To start movement, what I have to do is that I have to, use these transport layers. The first transport layer I call is ETL, and this is HTL. What is ETL stands for? ETL stands for electron transport layer, and this stands for hole transport layer. Okay, ETL, electron transport layer. HTL is hole transport layer. Now, just take a look. The electrons are here. The electrons cannot move in the right direction. This cannot go in this direction. Why it cannot go? Because there is a barrier here. Whereas the electrons can go here, right? Because it's energetically favorable for this electron to move from here to here. Okay, remember, electron is a stone, heavy stone, which wants to go down. So electrons cannot go up, but it can go down. So this electron will try to move here. Similarly, holes which are here in the active layer, which is a perovskite layer, it cannot go in the left hand side, but it can always go to this side. So this particular electron transport layer helps in the transport of the electrons, whereas this hole transport layer helps in the transport of the holes. Also, this electron hole transport layer blocks the electron, and this electron transport layer blocks the holes. And why it is important? It is important because if electrons and holes, both of them move in the same direction, there is no current. There will be no current. To have a current, to produce the electricity from a solar cell, the electrons and the holes have to move in the opposite direction. If you recall from my PN junction diode, the electrons are moving in this, some electrons and holes are moving in the opposite direction. That's how electricity has been produced. In the case of perovskite solar cell, there is no PN junction diode. So for the electrons and holes to move in the opposite direction, I have made use of these transport layers. Okay, and these transport layers, they should have this type of band element. Okay, we have to choose this electron transport layer and electron transport layer in such a way that their conduction band is near to this one, and the valence band is very far away from this one for the ETL. Similarly, for the HTL, the the valence band should be very much close to this valence band of the active layer, whereas there should be a mismatch of the conduction band of the HTL and the active layer. Okay, I hope you have understood it. So once we put the electron in ETL and HTL, the electrons will move here, holes move here, and then we put two electrodes, one electrode and one electrode here. What is the role of electrodes? Electrodes are there simply to collect the charges. So electrons are collected in this electrode, and this one, electrons are collected here, holes are collected here, and see, electrons are moving from left hand side, the holes are moving to the right hand side, and it constitutes the current. And this is the reason why we need electron transport layer and hole transport layer in perovskite solar cell. Okay. Okay, I hope that you have understood. Let's move ahead. Okay, now device architecture. Depending upon, suppose this is electron transport layer, this is hole transport layer. I can reverse the way as well. I can put the hole transport layer here and electron transport layer here as well. Okay, so I can have both the configuration. So depending upon the position of the electron transport layer and the hole transport layer, a perovskite solar cell can be of two types, PIN or NIP. Okay, now look at the direction of the current. The light. Light is coming from the bottom and it's going to like this. Okay, when it's going like this, what it sees first? It sees first the hole transport layer, because this is the green layer. Then I means intrinsic. Okay, this is the active layer or the perovskite layer, and this is the electron transport layer. So when light comes in, it first encounters the hole transport layer, which is the P-type material. then it encounters the perovskite layer, which is the active layer. This is the intrinsic material, whereas intrinsic material, and this is the pink is the n-type material, which is the electron transport layer. That's the reason why this is called PIN. Whereas in this case, when light comes in, it first encounters electron transport layer, the pink part. So we call it NIP. Okay. Both this configuration has their own share of advantages and disadvantages. Depending upon which configuration you like, you can work on both the direction. But nowadays, initially, people, in the initial days, this was more prominent. But nowadays, most of the perovskite solar cells are in the PIN configuration. Okay. Okay. Now let's compare with silicon technology with perovskite. Why do we need perovskite? We already have silicon. It is very efficient, very stable. It has already been commercially available. You can buy it from the Amazon as well. So why do we need some other technology? Let's try to understand. Okay. So silicon is a very high efficient. It's around 18 to 20%. In fact, in laboratories, inside the lab, inside the research laboratories, you can get up to 26% efficiency of the silicon technology. It is very stable. It has a lifetime of 20 years. So once you install it in your rooftop for 20 years, no tension. Of course, you have to keep cleaning on the surface so that no dust is there. You have to make sure that the light falls on the solar cell. But if otherwise, for 20 years, absolutely no problem. And it's a mature technology. Why mature? Because it is discovered in, the first silicon solar cell came up in 1953. So from 1923 to 2025 now, it's almost 75 years. So it's a mature technology. Whatever the drawbacks were there, they have already been overcome. So it's a very mature technology. It is already commercialized, very stable. So it's a win-win situation. It's very good. But there are some drawbacks as well. It is still costlier because to make silicon, you need clean room facilities. Clean room means it has to be very clean environment to make the silicon. They are thick and heavy. I don't know. Have you seen it in the rooftops? It's very bulky. It's very, you need 2-3 persons to move it around. It's very thick and heavy. Aesthetically not good, which means that it looks very, it doesn't look very beautiful when you install it in your rooftop anywhere. It doesn't look very nice, right? It's bulky. It's black in color. Not aesthetically, from the aesthetic point of view, it's not so good. And it is non-flexible, which means it cannot be bended. It has to be flat always. It cannot be installed in a curved surface. So it's non-flexible. But this is where perovskite technology comes in. This perovskite is very cheap. In terms of cost, is very cheap compared to silicon. And I have a video for you guys. I hope I will be able to run it. So this perovskite can be printed just like you print paper, print photograph. So this is solution processed. As you can see here, they have printed perovskite. Okay, so that's the reason why it is very, from the cost point of view, because you can print it, is very cost effective. Okay, compared to silicon, which needs clean room facilities. Some other properties, like it is flexible. As you can see, you can bend it. It can be of various shapes. It can be of rectangle, square, any shape. It can be circular, any shape which we want. It is very lightweight. It's not heavy. It's not bulky. It's very lightweight, as you can see here. And also it can be made semi-transparent. Okay, it can be semi-transparent. As you can see, the hand is visible from the other side. And also it can be colorful. In the case of silicon solar cell, they are always black in color. Aesthetically they're not good. But silicon solar cell, they are very lightweight, it's cost effective, flexible, can be of any size, shapes, and colors. And it also can be made transparent, which means they can be installed in our windows as well. Not only rooftop, but they can be also be installed in the roof in the windows. We will try to understand some more advantages in terms of energy payback time. So what is energy payback time? So if we just define it, so energy payback time, or EPBT, is the amount of time it takes for an energy system amount of time it takes for an energy system to generate the amount of energy equivalent to the amount that it took to produce the system. In other words, it is like doing a business. So if you have invested some money, how much time it will give you the money which you have invested. Okay. Now in the case of silicon solar cell, as you can see that you need at least close to 2.5 years to recover the money which you have invested for installing that silicon solar cell. Whereas in the case of perovskite solar cell, this is less than 6 months. So if you install silicon solar perovskite solar cell, the amount of time is very less compared to that of the silicon solar cell. So you can recover the money which have invested initially in very shorter period of the time. In terms of EPBT as well, perovskite solar cell are very good. Okay. Now, also, I have also put in the number of publications. So this is the year, and this is the number of publication of perovskites. So in terms of why also we want to work on perovskite, because perovskite is a very, very hot topic. As you can see, it was discovered in 2009. The number of papers which have a perovskite was only 5. And look at the number of papers right now. In 2025, which is not yet finished, the number of publications is 11,000. So more and more number of people are working on this new technology, because this is something which can replace the silicon technology. Okay. So this is also one way of looking into it, that, if you want to make an impact in the research community, you should work on the perovskite. What is another reason? Another reason is that the absorption. I told you, the more you absorb, the more chances of getting, converting that to photons, electrons, or the electricity. As you can see, this is a comparison of crystalline silicon, gallium arsenide, and perovskite. And as you can see, the perovskite has a higher absorption, which means it absorbs more light compared to silicon or compared to gallium arsenide material. Okay. If it absorbs more light, which means that it can convert the photons to more electricity. Okay. So this is one more advantage. Another advantage, you can tune the band gap. Okay. As you can see here, these are the 3 types of perovskite material. The difference is in terms of the halide, ABX3. I told you the chemical formula of perovskite is ABX3. So this is your A, this is your B, which is lead, and I is your X, ABX3. Now the difference between these 3 perovskite is only here it is I, here it is bromine, and this is here chlorine. Okay. By changing the chemical composition of the perovskite, you can tune the band gap. You see, this is 1.55, this is 2.3, this is 3. So depending upon the different applications, depending upon where do you want to install the solar cell, whether you want to make it a semi-transparent solar cell, or whether you want to make a tandem solar cell, you can tune the band gap. This is a very, very great advantage of perovskite as a material itself. Okay, this is the great advantage of perovskite over silicon. Silicon is band gap is fixed. You cannot change it. But in perovskite, by playing with the chemical composition, you can change the band gap. But the question is, if perovskite is so good, then why we are not using perovskite in our homes, in the streets or in the industries? This is a question which we must ask ourselves. Well, there is a reason for it. The reason is the stability. I told you the silicon solar cell, they are very stable. Once you install it for 20 years, absolutely no problem. It's stable, but perovskite is not stable. Okay, this is the only reason why why perovskite are not being commercialized yet. Okay, people are working on it. I am working on it. There are thousands of people are working on it. As you have seen, the number of publications is very high. They are all trying to make perovskite stable. Okay. The problem is that when we expose this material to sunlight, UV light, or higher temperature, it breaks down. It breaks down, and when it breaks down, we lose the photovoltaic property. Okay, it no longer can produce the electricity. Till right now, as I said, it degrades quickly and such. And if it's not so stable, means it is not good enough for commercialization. If you want to commercialize any technology, you need at least 5 years of lifetime, which means if I install perovskite-based solar cell in my rooftop, it should be able to give me energy at least for the 5 years. Okay. If it goes bad in 6 months time, then it makes no sense to install perovskite solar cell compared to silicon solar cell. It should be stable enough to at least for 5 years. Okay. Otherwise, I have to keep on changing my perovskite solar cell after every 6 months. Till now, people have researchers have got stability of 2 years, but it's a continuous work, and we are hopeful that in few years of time we will be able to make it sufficient enough, stable enough to make it commercialized. Okay. So don't think that it will not be stable anymore. Remember, when the first silicon solar cell came up, it was, how much efficient was that? It was 1 to 2%. And what is the efficiency now? It is 26%. So from 1 to 2% to 26%, it takes 100 years. And for perovskite solar cell, we are only 15 years old. So give us time, and we will make the perovskite stable enough to be used as a for commercialization. Okay. So how to fabricate solar cell in the lab, in the research lab? Okay, so you start with a glass with FTO coated. This is the transparent electrode. Many of you will not be able to understand what is FTO or what is what is the role of this one. But I don't expect you to, because it's 1.5 hours of talk. But if you want to know more, of course you can contact me. I will be able to. I can explain in more details. Okay. So how do we make? We take a glass which has FTO coated on it. Then we put the first layer, which is electron transport layer, by spin coating. This is spin coater. This is the solution. Then after the spin coater, we deposit the the perovskite material. In this case, this is MAPBI3. This is ABX3. This is a different type of perovskite. Again, we use spin coating. After that, we use pyrovomitate, which is an HTL layer, whole transporting layer. It goes on the top of this one. And finally, we use the evaporator to deposit the final electrode. Okay. So so what type of solar cell is this? So light comes from the so light comes from the bottom, from this side. So this is ETL, this is NIP. So this is a NIP configuration of perovskite solar cell. Okay. The top this FTO and this copper is your electrode to collect the electrons and holes. ETL and HTL, which is pyrovomitate, is the material for the transporting layer, whereas this MAPBI3 is your active layer, which is the perovskite material which converts the photons to electrons and holes. Okay. How does they look like? Actually, this is the samples which we have prepared in our lab. This is a solar cell looks like. This is the big area. This is the small area ones. Okay. And light comes from the bottom. As I said, this is the NIP configuration. And all these solar cells are made inside this glove box, because as I said, this material perovskite is not so stable. So we have to make it inside the glove box. A typical glove box looks like this, which means what is a glove box? Glove box is nothing but it's a control environment. It has only nitrogen inside it. It doesn't have oxygen, because oxygen makes the material unstable. So we only have nitrogen inside it. So we make the solar cell inside. And then how to characterize it? We use solar simulator, because ultimately we have to test our solar cells. How to test our solar cell? We cannot take our solar cell and go outside the sun. If it is a rainy day, I cannot test my solar cell if I go outside. So I need a solar cell inside my lab. So this is a solar simulator. This is the light which is coming from the solar simulator. And as you can see, this is a white light, which is exactly the same light which you see in the sun. So this is an artificial sun inside the lab to test our solar cells. Okay. So we put our solar cell here, shine it, and we measure the, as you can see, the cables are connected here to get the IV characteristics. Okay. IV characteristics. And once we get the IV characteristics, we can calculate the efficiency of our solar cell. There is one more equipment which is called the quantum efficiency. This is how a quantum efficiency equipment looks like. Basically, what does a efficiency looks like? What is quantum efficiency? Quantum efficiency, nothing but so on x-axis you have wavelength lambda, and y-axis is your quantum efficiency. It basically measures how much efficient your solar cell is against each wavelength. Okay, against each wavelength. As you can see, so if it is a lower wavelength, the efficiency was less. It's in this region, it is quite close to 1. So my solar cell, which I'm testing here, is more efficient in this part of the spectrum, whereas it's less efficient here and here. Okay, so this is how we characterize our solar cell in quantum efficiency. Okay, So with this, I would like to conclude here. It's around 1 hour 15 minutes. I kept the last 15 minutes for any questions or doubts, any more details which you want. You know, I am in IIT Dharwad, not very far from Haliyal. If you want to visit us, please let me know. Give me an email. We can arrange a talk, lab visit. You can see by your naked eye how solar cells are made inside the labs. What are the different phenomena? How do we measure it? How do we characterize it? My students or postdocs are here. They can help you to understand. So feel free to write to me in case you want to have a lab visit. So I like to thank you, and I will be I'm here to answer any particular questions or doubt for any one of you. Thank you.
Thank you so much, sir. Thank you very much. Dear participants, if you have any questions, you can either post it in the chat box or you can ask directly to Dr. Ghosh, sir. Go ahead.
Looks like everybody understood it.
It was a nice presentation, sir, indeed.
Thank you. Any question? Don't be afraid of asking questions. Don't be afraid of asking silly questions. I am open to any questions
sir.
you have. Yes.
Yes, madam. Please go ahead.
Yeah, sir. Myself, Dr. Pushpalata from Cambridge Institute of Technology, sir.
Okay.
Are
Please.
you hearing me, sir? Can you hear me?
Yes, I can hear
sir,
you.
You said you have postdoc students.
Yes.
Sir, can we do postdoc part time also?
Postdoc as a part time.
As a correspondence or part time, like how do we do PhD? Is it available in IIT in your?
Yeah, I mean, it will be not paid.
Okay.
That will be the difference. Okay.
Okay. No problem. Like,
yeah.
When we are doing part time means.
So it means that you want to visit sometime in my lab, do some experiments, and you go back to your home and do some analysis, and that is always available. That is, you don't need to be postdoc. That can be a collaboration as well. You want to learn something, you can come and visit. That's not a problem. It's not like postdoc exactly, but if you want to more, but it will not be paid because it's a part time.
Okay, and no problem, sir. Like I will get to that. I will come to know that I will get the postdoc certificate, right? Like I have done postdoc, part time only.
Yes. If you have visited my lab and spent some time here, then then it is not a postdoc, because postdoc is always a full time. Postdoc cannot be part time. PhD can be part time or full time, but postdoc is always full time. So it's like it's not about certificate, but you can say that you collaborate with Dr. Ghosh, in his lab or something like that.
Yeah, that is a collaboration work. But
yeah, it's a collaboration.
in Mangalore, sir, there is a Srinivasa University. So I think there it is available postdoc part time.
Okay,
So,
in IITs it's not possible. In IITs it's not
IITs
available. Yeah.
Okay, sir. Okay, fine, sir. Thank you.
Usually, private universities offer, madam, part-time postdoc also, but in IITs and NITs, I guess it is they don't have such provisions, I guess.
Yeah. Okay, sir. Fine. Thank you.
Thank you.
So, till now, the efficiency of the solar cells is not beyond 30%. Am I correct, sir?
Single junction solar cell, yes, single junction. So there is a theory which is called Shockley-Queisser limit. This is a theory which says that if you have only one kind of active layer, you cannot go beyond 33%. So this is a theoretical limit. But if you combine 2-3 active layers, there are solar cells which can go up to 40% as well. Okay, and those type of solar cells are used in satellites.
Yes.
Yeah. But if it's only one type of solar cell, or say silicon or perovskite or organic, it cannot go beyond 33, theoretical limit.
Yes. Sir. Okay, participants, if you do not have any other questions, then it is the time to express our gratitude to today's resource person, Dr. Dhriti Ghosh sir, on behalf of all the participants and on behalf of my esteemed college management, KLS, and on behalf of our beloved principal, Dr. V.A. Kulkarni sir, and on behalf of all my colleagues here, I wholeheartedly thank Dr. Ghosh sir for sparing his valuable time with all of us and engaging. It was really engaging session, sir. We have all, as you said in your introductory comments, that at least by the end you will come to know what is the difference between ordinary solar cells and the roadside solar cells. Yes, you made definitely a point, sir. And thank you so much, sir. Thank you very much for being there. And hope these interactions will continue further. And since you have, graciously invited participants also, and especially me as a host institution, I will definitely take this opportunity, sir, to visit your institution and visit your lab in particular, and definitely with my students, sir. We
Yes,
have
I mean, it will
first
be
year.
great if yeah, it will be great if you all can come.
Yes, sir,
Not in
yes.
very big numbers, but in small groups. If you can come, and I will be happy to show you my lab. How solar
Yes,
cells
sir,
are
yes.
made. All those things.
Yes, sir, definitely, definitely, sir. I will be there, sir. Thank you,
Yeah,
sir. Thank
great,
you very much.
great,
Yes,
great. Thank you for invitation. Thank you,
thank you very
thank you.
much, sir. Okay.
Okay, bye bye.
Bye, sir.
And anyone who wants to any questions, privately also they can mail me.
Yes,
If you have any questions or any doubts, you can reach out to me over in my email.
yes.
Okay, thank you, thank you.
Thank you.
Bye bye.
Thank you very much. Bye, sir.
Bye bye. Bye.
So, dear participants, you have 8 minutes of break now. Our next speaker, Dr. D.P. Singh, sir, will be joining in just. DP, sir, are you there? So participants, we can go for a break, have tea, and come exactly at 7:30. Next session will begin.
Yes, no, no.
नमस्ते सर।
हेलो, नमस्ते नमस्ते सर, कैसे हैं आप?
बढ़िया हो सर, थैंक यू सो मच। हमारे
थैंक यू। हेलो, योर माइक्रोफोन इज ऑफ।
So yes, yes, sir. Thank you, sir. Thank you. How are you, sir? Fine.
No, thank you so much. Thank you so much for the invitation. Although it was a little far from the field, but yeah, so that's. So please let me know when to share the screen and when to start. So.
1 minute to go, sir. You can relax.
Okay, yeah. Please take your time. Yeah.
Yes, sir. 1 minute.
It's more. Oh, it's not single.
So I will text you if I need.
Yes, yes.
Thank you.
Sir, it is time now, sir, 7:30. With your permission, shall we start, sir?
Yeah, definitely. Yeah.
Yes, sir. Good evening once again and welcome to all the dear participants. The second session is about to begin, and for this session we have with us eminent personality, Dr. Dharmendra Pratap Singh Ji. It would be my immense pleasure and honor to introduce to all of you to today's personality, Dr. D.P. Singh sir. Dr. D.P. Singh sir is an associate professor at ULCO, France. He is a member of the Unite Dynamic and Structure Material Molecules Laboratory and head of the first year cycle of Industrial Engineering at the Engineering School of the ULCO. Dr. Singh obtained his PhD degree from Department of Physics, University of Lucknow, India in the year 2016. His current research activities are focused on the columnar materials, discotics, ferroelectrics, pneumatic, and ferroelectric pneumatic liquid crystals, along with their nano-dimensional counterparts. For studying the charge transport mechanisms and their applications in energy, sensing, thermoelectricity, optoelectronics, photovoltaics, and organic electronics. In the coming this month only, he will be receiving the Silver Medal Award from Indian Liquid Crystal Society in this month of November 2025. He received the Young Scientist Award from the Indian Science Congress in the year 2017. He is the recipient of the Best Research Award by the Indian Liquid Crystal Society in the year 2012 and SPIE Early Career Award at Cambridge University in the year 2013. He was also awarded the Best Research Award by the Korean Display Society in the year 2015 and the prestigious Raman Charpak Fellowship in 2014 to work in France. He has published more than 115 research articles in esteemed journals and 4 book chapters. He is also the principal investigator of many projects such as PSC Star, ProCore, Haliyal, Alliance, and Samuel J. Chaplin with South Korea, Hong Kong, Italy, the United Kingdom, Poland, Belgium, and Canada, respectively. Presently, he is serving as a reviewer for more than 40 reputed journals from RSC, ACS, APS, Wiley, Elsevier, AIP, IOP, Springer, Nature, etc. He is also a lifetime member of the International Liquid Crystal Society, the Indian Liquid Crystal Society, and an affiliate member of the RSC and APS. He is also serving as the guest editor for the journals published by RSC, Elsevier, Wiley, and Springer. With these brief words, I now present before you today's speaker, Dr. DP Singh sir. Sir,
Okay. Thank you. Thank you
thank
so
you
much. Thank you so much, sir,
for being there.
for the kind introduction. And now I will share my screen. So
Yes, sir.
hope it is visible for all participants.
Yes, sir. Yes, sir.
So first of all, thanks to you and my colleague MS Mansankar for the kind invitation. And it is my pleasure to be the speaker in this faculty development program. Unfortunately, I couldn't come in person, but it is my privilege to join it online. So as you know that I am working as associate professor at the Université du Littoral Côte d'Opale in France. So this is a public university in France, in north of France, close to England border. And yeah, now my field of interest in research, they are basically the organic semiconducting materials. So here today I am going to talk about some organic semiconducting materials and their successive application in optoelectronic devices. We are also doing some work on the energy storage in and energy conversion. However, the application is totally based on the organic material. So basically here is the outline of my talk. So I will briefly introduce you about the background of my domain, and then I will give you a brief introduction of the liquid crystal material, organic semiconducting material. So basically liquid crystals are the organic semiconducting materials. I will also present some of my recent research result which we have obtained in collaboration with a different project under different partnership. And at last, I will give you some conclusion and future perspectives. Of course, you can carry some lesson to home and think about the current problem of these fields. So before going to the scientific content of the talk, here I would like to show where I am situated in France and Europe. So as you know that France is situated here in the Europe, and this is my city that is called completely a coastal city and known as Calais. So basically, this is my laboratory, and the laboratory is situated in three cities. First one is Dunkirk. So you might have seen the movie Dunkirk, which was released in 2015, based on the Operation Dynamo from the Second World War. And this is the Calais where principally I am situated. Calais is also a very historical city, and it is known for a sea tunnel that connect France to the England. So this is England. This is the European border of France, which is a part of European Union, and in between only 33 kilometer of English Channel is there. So these are the sites of my laboratory at the Calais, Saint-Omer, and Dunkirk. So if you are interested in the activities of UDSMM, you can go to this website and you can come to know what are the current research interests of the different faculty members. So obviously, like as I told you that I am situated in the coastal city. So obviously these are the beautiful panoramic views of this Calais city. For example, this is the top view of the city, and this is the town hall, and this is the area of port, because Calais is one of the very important center for the sea trade in European Union. And these are the some outskirts of my city, and they are called Cap Boulogne, Cap Green, and from where you can see the England weather is very clear. And very recently, a very nice example of artificial intelligence has been installed in our city, that is called the Dragon. And obviously, you can ride this Dragon, however, it's not real, it's artificial. And nowadays, after installation of this Dragon in the city of Calais, we are also known as the Dragon City of France. Okay, so now coming to my research interest. So basically, I am working on organic semiconducting material, particularly on liquid crystal material. So we use different type of organic semiconducting material for the different purposes. So the one purpose is like selective detection and sensing. And the second, using the disk-like semiconductors, and we are using those for the organic photovoltaic devices, organic light emitting diodes. And very recently, we have started 3 years back a new domain of these organic materials for the energy storage system. So basically, the idea is to replace these lithium ion and sodium ion batteries with the organic batteries. So obviously, this is the very starting phase of the organic batteries. Also, I am associated to the European network, which work on the ferroelectric pneumatic phases. So basically, this is a new phase which was discovered in 2019, but first time it was recognized in 2020. That is known as the ferroelectric pneumatics. So basically, you know about the solid state ferroelectrics, which have microcoulomb order of the polarization. However, the soft materials, they have the polarization in the nanocoulomb order. However, these newly developed material, they are showing the polarization in the microcoulomb order, that is equivalent to solid state ferroelectrics. So obviously, this is the very new phase in the child stage. So when it will grow, obviously it can change the world of ferroelectrics. So at last but not least, I also work on developing some non-toxic nanomaterials, especially the quantum dot materials, and their successive applications in the field of energy, biomedical sciences, and environmental applications. Because every year in France, every 5 years, there is a theme of research. So we have to align all of our project along that theme. So if you are interested more or our result and our research domain, you can go through our recent publications. Some of the publications are listed here, and do not hesitate to write me or to connect with me if you are interested in our activities, and if you want to do any joint activities with my group or my laboratory. So obviously, first of all, I will show you two slides that why displays are very important, because this is also one of my domain. So many of you have already known about the CRT screen that were based on the cathode ray tube, and the electron deflection was taking place according to the magnetic field what you applied there. And then you could see the monochromatic things, or black and white in color on the screen due to the fluorescent screen. And later on in the era of 1950s, you could see the color CRT screen. What happened? A revolutionary investigation took place in the era of 1970, when LCD, that stand for the liquid crystal display, was developed. And first time it was developed with the TNC LCD, that is known as twisted pneumatic LCD, liquid crystal displays. So obviously, this discovery was very important for the display industry, and almost for the 2 decades, these liquid crystal display devices, they captured almost all the display market, until and unless they were replaced by the OLED based displays. And nowadays, ultra high definition, curved high definitions based displays were also evolved from 2003 to 2014. Later on, the most recent technology in the display devices is quantum dot LED TVs. So however, there are still some challenges in this technology. However, the cost of these equipment or display devices is very high. And the most recent applications of these curved or foldable display devices were developed by LG and Samsung, and you can see this foldable mobile phone in the market was launched in 2020. So obviously that this took a long way to come to these foldable devices. So if you are more interested about learning these display devices and how they work, their functionality and so on, you can go to my book chapter, which I have written in collaboration with my colleague SK Gupta. So obviously that many of the researchers, they think that now the display industry using liquid crystal molecules has been saturated. However, it's not completely true. So here you could see a curve, a representative graph that has been done by the data bridge market research things on the LCD market. So you could see here that not only the developed country, but also developing country and low income countries, they are still focusing on the LCD based displays. So the liquid crystal based display are still in the competition with the newly developed technology like QLEDs. So still there is a chance of the competitive business, as well as you can have plenty of space to develop some new applications using these liquid crystal materials or organic semiconducting materials. So who they are not aware with this field, for them, I would like to tell you a brief introduction about what are the liquid crystal. So basically, all of you had already studied in the high school or before high school that there are three states of matter, that is solid, liquid and gas. So basically in the solid materials, what happens, these atoms or molecules, they are arranged in a well proper manner following to their crystallographic conditions. So for example, if you take the example of one crystal, so here you could see that atoms are well arranged in a different array. So due to their well orderedness, their order parameter is equivalent to 1. And then if you talk about the isotropic liquid materials, where atoms or molecules, they are randomly oriented in all possible directions, and that's why their dipole moment is uniformly distributed over all the directions and making the overall dipole moment 0. So they do not have any order at all. That's why order parameter is 0. Okay, so what is the physical representative physical property of this crystalline or solid material? So that is elasticity. And if you talk about the liquid material or any isotropic liquid, so they have two basic properties. One is called viscosity and another is surface tension. So there can be some material that can have properties like elastic properties like solid, and isotropic like viscous property like isotropic liquids. So these intermediate materials are known as mesophase materials, and their phase is known as mesophase or liquid crystalline phase. Liquid crystal word is a combination of the properties, like it works like liquid also and crystal also. But however, the obviously the order will be lesser than the crystal and isotropic liquid. Okay. So in the liquid crystal material, basically nematic phases and schematic phases are the two principal phases. So in the nematic phase, these molecules are oriented along a preferred direction, and this preferred direction is known as the director. So in this situation, in the nematic phase, these molecules only have the orientational order parameter because they are oriented along a particular direction. What happen if they are molecules are also arranged in a particular direction and also in a particular position? So when they have definite degree of positional order parameter, they are also arranged in the layered structure. You could see here, these are the layered structures. So in this situation, these phases have the orientational order parameter as well as a weak positional order, and that is like referred as schematic A phases. So obviously that depending on the molecular geometry and the crystallographic conditions, molecule will be arranged in any type. So for example, if molecules are tilted as compared to the layer normal with an angle theta, so this makes schematic C star phase. So obviously, as I told you, that order parameter of this liquid crystalline material or organic semiconducting material is lying between the crystalline solid and isotropic liquids. Therefore, their order parameter lies between 0.2 to 0.8. Okay, so now if you how these materials are very important and why I am very fascinated to work on this material. So if you see these crystalline material and isotropic liquid under the polarized optical microscopy, so you have the crust condition of polarizer and analyzer. So crystal will be like you will see a very nice optical texture, but it will be like it will have not too much birefringence in the texture. So because it will have a definite dipolar contributions of the molecules, so you will see some colors. However, these colors will not be changing with the as a function of temperature. And if you see a liquid material, that it will look completely black because molecular dipole will be randomly distributed. So there will be no preferred dipole moment here, and you will not see anything here. So it will be black in color. However, when you put the liquid crystal material under the crossed polarizer analyzer condition, what happens, you can see very nice optical textures of these materials. And by analyzing these optical textures, you can differentiate which phase is this. So this is my personal web page, and if you are more interested in knowing my current research activity, you can also check on that. Okay, so here I would like to show you that how when you heat a liquid crystal material, how it goes from crystalline solid to a liquid crystal phase, and then how it goes to the isotropic phase, that is liquid phase. So here there is a small video. So when you heat a material, now this material went to liquid crystalline phase, and this liquid crystalline phase, you could see here very nice optical birefringent textures with some defects. So obviously, if it have one phase, then it will go to one phase, and then it will go to second phase before going to the isotropic phases. And yes, if you are mathematics, if you are from the mathematics background, obviously you can do a lot of simulation and mathematical treatment of these defects, because here the singularities and singularity at the defect, different type of defect, the singularity will be changed. It can be +1, -1, +half, -half, and so on. So you can do this. And when it will go to the isotropic phase, this texture will be converted completely in the black. So now this material went to isotropic phase from the liquid crystalline phase. So obviously this observation of phase is completely reversible. So when you cool the material, it will again come to the liquid crystalline phase, and then it will come again to the crystal phase. So here first time like we had a project with our Korean partner, Professor Yongki Kim, at postdoc in Pohang. So with that, we has investigated the selective detection using our rod-like molecule, and also when these rod-like molecules are coupled with the non-toxic quantum dots. So these results are very recently published in Advanced Optical Materials. So before I would like to show you just some fundamentals of this selective detection processes. So why we can have a selective detection using some particular material? This principle is associated with light matter interactions. So basically, light matter interaction can be explained by the green function. Okay. And in this situation, there can be two regimes. One can be the weak coupling regimes. So weak coupling regime can be mathematically expressed with this formula. And in the weak coupling regime, the losses dominate over the coupling, so that the light interact with matter uh, without any coherent interactions. So in this situation, the coherent interactions are almost unable to find. And when in contrast, when you have the strong coupling region, so in strong coupling region, what happens, these losses are not so dominative. So in this situation, the coupling is basically characterized by coherent interactions. Okay, so here I just want to quote a quotation that was written in Isa Upanishad. So basically, recently I come across this, and obviously I am not going to read in this what is written in Sanskrita, but its English translation is, whatever exists in this changing universe is pervaded by the consciousness. This means, like, because green functions are always the temperature or time dependent. So this means, like, when this light is interacting with any material, it will show different properties. So obviously that this principle is used in our organic materials, and these materials basically show a p-type behavior or n-type behavior, like semiconductor materials like silica and so on. So, the first, like, I will show you that how and what is the principle behind this selective detection and sensing purposes. So, okay, so liquid crystals, basically they are optically active. So when light passes through these materials, they show the birefringence nature, and the property changes depending on the birefringence degree of these materials. So first of all, because all liquid crystals are optically active, and these liquid crystal materials, they have orientational property, because you can change the orientation of these liquid crystalline material by applying the field and surface treatment. And they are also electrochemical responsive nature. That's why they can be used as liquid crystal sensors. So this is one field which has been emerged in the last decade. And not only the physical sensor, that nowadays even every type of sensors can be fabricated using liquid crystalline material. So here is the simple principle I am going to explain, that what is the basically principle of the detection using liquid crystal material. So for example, if you want to detect any analyte, okay, so what will happen, that you have to prepare a substrate and you do surface treatment. So blue color layer is like surface treatment, because either you can orient this liquid crystal material perpendicular to this substrate or parallel to these substrates. So if liquid crystal molecule, this is represented in a orange color. So when it is oriented perpendicular to the substrate, you will not be able to see any image like bright state or birefringence optical textures under the polarized optical microscopy. So when there is no analyte is present, all the liquid crystal molecule will be perfectly oriented perpendicular to the substrate, and there will be no any optical textures. What happens when any analyte is present? So when you want to detect any particular analyte, you have to put some analyte here, and then analyte will interact with these liquid crystal molecule. So the liquid crystal molecular orientation will be changed from perpendicular to planar or any tilt, then, and then the optical image will be changed. So here you could see the black color, that there is no birefringence at all, and here you could see some degree of birefringence. So this is called homeotropic condition, and this is called the planar condition, and then you can detect the presence of any particular analyte. Okay, so this method is very simple, because how you can do it here, you can take any glass slide and you can do the OTS surface treatment, and then you can have any targeted molecule or analyte to whom you want to detect, and then when you will put in between this OTS modified glass slide, and then liquid crystal orientation will be changed, and you can detect any particular analytes or any other moieties. So here is one another approach that you can do another things. You can detect the change in liquid crystal molecular orientation at the interface, aqueous interface, or air water interface. So what happens in this situation? You can fill the liquid crystal molecule in between two grids, and these grids you can prepare by the photolithography, and the width can be like from 5 micron up to 100 micron. So first you fill here the liquid crystal molecule, and then you can put some any surface agent or anything, and when your analyte will be, or targeted molecule will interact with the liquid crystal and at the interface, then it will change the molecular orientation, and you can analyze this on the TEM grid. So TEM grid is a very fine example of this type of arrangement, and you can make your sensing device using liquid crystal material. So why we were also interested doing this, because France and South Korea, they have large area, that large coastal area especially. So in the coastal area, one of the challenging problem is the water pollution. So actually water pollution is basically driven by the lead, mercury, and metal elements. And because this Calais area is one of the very busy sea route. That's why we sometime here the local government is more interested to monitor real-time monitor of the water quality. So why we just look into the literature, and we found that there were very nice landmarks of liquid crystal based sensing. So first it was the group of Nikolai Abbott from United States. So first time he presented liquid crystal materials to for the sensing purpose, and this was reported in the Science in 1998. And in this report, he found some optical amplification of ligand receptor binding using liquid crystal material. So this was the first report. This was the first report which represented the liquid crystal based sensing. And consecutive after this first report published in Science, he continued the research in 2001 and 2002 by publishing two more papers in Science, which stabilized the fact that these liquid crystal material can be used for the sensing purpose. And now this field is very stabilized field. So now the question arises how it works. So basically a thin film of liquid crystal is basically sandwiched between two glass plates. Glass plates will be, obviously it will be functionalized just to give a particular orientation of to the liquid crystal molecule, so that liquid crystal molecule either can be oriented parallel to the glass plate or perpendicular to the glass plate. But basically we orient them perpendicular to the substrate. And in the absence of analyte, LC molecules remain uniformly aligned. For example, we say vertical alignment or homotropic alignment, giving a predictable dark state under the crossed polarizer analyzer condition. In contrast to this, when your analyte is present, it will bind with the layer of liquid crystal molecules, and in this situation they will disrupt the LC alignment. So now alignment will be changed from vertical to planar, and then you will receive the change in birefringence, and by analyzing the change in birefringence you can estimate, or you can analyze the change, like uh, you can sense a presence of a particular analyte. Okay, so basically like these reports like gave us inspiration for this project. But there was very important factor that why we are choosing some particular element only. So at our first effort, we have chosen the arsenic to detect. Now the question arises that why only the arsenic one? So obviously there are some other also like lead, mercury and so on. But in the first effort, we targeted on the arsenic one. Why? Because arsenic can be present in different oxidation states. So here arsenic third is very poisonous, which is basically present in the water and soil. So these arsenic 3 is absorbed, obviously it's absorbed in the body, because it can be mixed very easily with the water and soil. So water and soil will be contaminated, and because we human beings, not only human beings, some other species also, they are continuously in touch with water and soil, so our body will be contaminated as well. So basically WHO has given some limitations of these arsenic, that how much quantity of arsenic should be present in water and food so that it will not affect the human health. So arsenic limit in the drinking water is 10 ppb, 0.1 microgram per liter, while in food it can be present 0.5 to 2 ppm in the food, in the beverage. However, if the our body is exposed for the longer time with the arsenic 3, it can affect our body, and obviously it can result in some skin diseases, lung cancer and skin cancers. So basically, why arsenic 3 is very important? Because arsenic 3 is basically dissociated from the sodium meta arsenite, and which is the main source of arsenic 3, and this, from this compound arsenic 3 is highly soluble in water. And also because this arsenic 3 is present in the pesticides which are being used in the agriculture, and now a lot of people, not a lot of farmers, they use the pesticide to grow the rate of their cultivations in agriculture. So obviously the high concentration or high amount of these arsenic can affect. And according to the most recent report of the WHO, that around 140 million people has been affected with the excess of arsenic. So to cope with this arsenic detection, and to make some very easy devices to detect the arsenic in drinking water, first of all we prepare some carbon dots from the biomasses. And because these carbon dots, because they are derived from the biomass, so they will be having no toxicity. Because if you derive any nanomaterial from the chemical method, obviously they will have certain toxicity and it can affect your body and environment as well. So what we have done, because as I told you that you have to do certain functionality for to these carbon dots in order to detect the arsenic. So first of all, we have functionalized these C dots to detect arsenic, and the functionalization compound was L16, because L16 is why we have chosen. You can choose another compounds as well, but why we have chosen L16? Because this is very cheap chemical product, and then we functionalize these C dots with L16, and because this is an easy process as well. So obviously we have characterized this this functionalization by different techniques. First, by using by the TEM, because TEM is one of the suitable technique to detect the effective diameter of these nanomaterials, because obviously their size, their diameter is in the nanometer order. In nanometer order, basically quantum confinement effects are taking place. So due to the quantum confinement effect, when you change the size, then obviously the electronic property and optical property are being changed. So here, when you functionalize these carbon dots, then obviously the effective radius will be increased. So you could see here the effective diameter of the synthesized carbon dot was around 4 nanometer, and when it was functionalized by L16, the effective diameter became 4.29 nanometer. So this represents that something is binded over the surface of carbon dot. And later on also we did FTIR in order to prove that the functionalization has been done successfully. Okay, so here this is the mechanism basically how we have done the selective detection. So basically what happens here you could see that we have iron liquid crystal molecules in between the micro wells. Okay, and here this is the mechanism we have represented that how arsenic molecules are interacting with the L16 molecule. So basically three L16 molecules they connect with one arsenic molecules via this mechanism. And if you see the mechanism of the change of alignment, so for example, if you have taken this water and liquid crystal interface, so here you could see here the birefringent textures that is giving the planar orientation. And when L16 is present here, you could see that there is no too much change here. So obviously L16 is not stabilized at the LC aqueous interface, but its presence show a significant orientational coupling with the liquid crystal molecules. So later on, what happens here we have come to know that how arsenic will be binding with the L16 atom. So please remember here NPT is just a representation for the carbon dot or nanoparticle this. So NPT is stand for the L16 functionalized nanoparticle and templating. So what happens? So here basically these detection method basically they don't they are based on the interaction between the analytes and your principal moieties. So basically hydrogen bonding or weak van der Waal bonding are responsible for that. But here first time we notice that this linkage is not driven by hydrogen bonding or weak van der Waal forces. Here is a covalent bonding between arsenic and oxygen. So what happens? So for example, we have done a plenty of experiments to show that we have selective detection like that. So here we also use one surfactant. So basically surfactant imposed homeotropic orientation to the liquid crystal molecule. And when and this we have taken the D tab as a surfactant. And when you have some external moieties, then obviously it will change the molecular orientation. So here texture changes from homeotropic to planar, and we can detect that. So later on that we have explained that which uh, principle is behind this change in molecular orientation. So basically two mechanism can be behind this change. The first mechanism is the change in the preferred orientation of the LC, that is called the EG axis, and second a decrease in surface anchoring energy that permits the reorientation of interfacial LC to minimize the elastic energy. So here the surfactant, as I told you, that surfactant impose homotropic orientation, and when moiety will be present, then it will change into the planar alignment. So for example, here in the first row, you could see when it is present with the D-type solution and liquid crystal interface, it is giving your the planar alignment. However, when you add the arsenic three molecules, the planar alignment changes into the homeotropic alignment. So, okay, to confirm which mechanism is really responsible for that, we have repeated the same experiment. However, here instead of using DMAOP glass, we have used the rubbed PI glasses. So basically PI is the polyimide layer of any polymer which orient liquid crystal in a planar or homeotropic manner. So here we have taken the planar orientation of the liquid crystal molecule, and look here at the D tab liquid crystal orient interface, and here is only the planar orientation is observed. And when still you use this arsenic molecule, so there is no change at all. So when there is no change at all, even after the presence of arsenic item, then we realize that basically change in the preferred orientation of the LC axis is a responsible mechanism for this change in optical texture of the liquid crystal materials. So, okay, so this is the conclusion of part one. So basically optical activity and external stimuli responsive nature of the liquid crystals make them suitable for the selective detection. So using the same principle, you can detect the arsenic, lead, mercury, etc., whatever you want. However, you have to do the functionalization of that so that the functionalization ligand capping can interact positively with your analytes to whom you want to detect. And basically the mutual interaction between the molecules, quantum dots and analytes plays a vital role for the detection limit. So for example, the detection limit which we found in our experiment, it is quite comparative with the present sensor available in the market. So obviously that if you want to develop a new technology, obviously you have to improve the detection limit and so on. And the detection limit of these sensors that principally depend on the mutual interactions of the analytes with your molecule or any layer which you use in the sensor. So okay, so here is my second part of the talk. In the second part of the talk, I will introduce you some of the organic semiconducting material, especially these materials are arranged in the columns, and how we have used this organic semiconducting or columnar material into the optoelectronic devices. So before I go to this topic, I will again give you brief introduction of this field. So basically, all these systems represent this supramolecular system. So these systems are known as supramolecular system. So a supramolecular system is nothing but it's a self-assembling system of the molecules or molecular subunits that are organized via intermolecular interaction. So basically all the colloids, meshes, liposomes, biological membranes, etc., they are the part of supramolecular system, including the liquid crystal material. Okay, and these supramolecular system also they show very nice light matter interactions, and their physical and chemical properties they are associated with their light matter interactions. So why I am fascinated to do this research, especially on this disc-like molecule, because the discovery of these molecules and this phase was carried out in India. So it was done by the S. Chansekhar and his colleague at the Raman Research Institute in Bangalore. So in fact, before this 1977, this year, it was a myth in the soft condensed matter that only a rod-like molecule can make mesophase, because in the rod-like molecule you have the best equilibrium condition between the elastic property and viscous property, giving both type of properties, and they results into the mesophase formation. So obviously that I come to know after working in France, I come to know that at the same time when S. Chansekhar and colleagues were presenting their work and they published in 1977, however, the group led by the Billard at the laboratory in France, in Orsay, they were also working on the similar type of compound, and in just the next year they published also their first report on the discotic liquid crystal. However, this report was published in French, and that time journal's name was Nouveau Journal de Chimie, and which is known as New Journal of Chemistry at this moment, published by the Royal Society of Chemistry. So why this was the first report on discotic liquid crystal, but why these disc-like molecules are very important? As I told that in the beginning of the slide, that only rod-like molecule were presenting the mesophase, but after this discovery, it was established fact that not only the rod-like but disc-like molecule will also show the liquid crystalline property. So as far as their geometry and chemical structure is concerned, it constitute a pi conjugated core. because pi conjugation is very important for organic electronics, because it will release the electrons and electrons can propagate in the device, which is the main necessity of the electronic devices. Okay, and this central core will be covered with the peripheral alkyl chain or some functional group depending on the condition. So you could see here, thanks to the chemist who has developed more than 70 cores, you could see here the different cores, and depending on these cores, more than 3600 disc-like columnar materials has been developed and investigated by the physicists. So why these materials are very important? Because these materials are self-assembled. Self-assembled means they can self-organize in any matrix. So here you could see here that how the rod-like molecules are self-assembled. So if you take a rod-like molecule, so this is cyanobiphenyl-like molecule, and when they are in a particular condition, they can constitute the nematic phase or schematic phase. So if you talk about the schematic phase, this is the molecules in which they have the a particular orientational order, and they are also arranged in the layer structure, so they will have the positional order as well. So here, you know, these molecules, they are forming the one-dimensional schematic phase, and following to the one-dimensional schematic phase, they exhibit two-dimensional charge transport along the long molecular axis and along the short molecular axis as well. So in contrast to these collimatic material, if you talk about the disc-like molecule, so disc-like molecule, they self-assemble into columns first via pi-pi stacking. Please remember that this pi-pi stacking and arrangement of self-assembly arrangement of this disk-like molecule is completely spontaneous. You cannot influence this pi-pi stacking as well. And depending on the geometrical condition and the other conditions, environmental conditions, they can be arranged into hexagonal matrix, rectangular matrix, oblique matrix, and so on. This depends on the crystallographic conditions. And as these phases are formed 2D columnar phases, and in 2D columnar phases, these one-dimensional charge transport takes place. So there can be different phases of this discotic material, like they can be arranged in the nematic orientation, in the columns, and so on and so on. And depending on the crystallographic conditions, as I explained before, they can be arranged into different phases like hexagonal, plastic, rectangular, helical, oblique, lamellar, and tetragonal as I. So in the part second, what we have done, we have used these columnar materials into the optoelectronic devices. So before I go to the our practical applications, what we have done at our laboratory, I would like to tell you why these materials are important, how this geometry is very important for the optoelectronic devices, organic electronic devices, and photonic devices. So, as I told you that these matrices are formed first with the disc-like molecules. So, first one disc-like molecule, they are arranged in a column, and then they are arranged in a hexagonal matrix, for example. So in these molecules, they have the conducting or semiconducting core and the alkyl chain, which is just a aliphatic chain like CnH2n plus 1, and they will be insulating in nature, and they will have some other functional group as well, making them electron deficient character or electron rich character. So if you talk about the geometry, so here you could see that the distance between two consecutive columns is around 20 to 40 angstrom, and the interdisk space is between 3.4 to 3.7 angstrom. So what happens that electrons or hole, they hop from one disk to another, and then quasi one-dimensional charge migration takes place in this type of materials, and exhibiting very interesting carrier mobility, charge carrier mobility up to the order of 1 centimeter square per volt per second, and very high anisotropy in electrical conductivity in the order of 10 to the power 5 to 10 to the power 10. These materials has been utilized in making the TFTs, photovoltaic solar cell, photoreflectivity, one-dimensional conductors, photoconductors, gas sensors, and LED, and so on. So now how these materials can be used in organic semiconducting devices. So basically, these devices can be your solar cell or organic field effect transistors. So for example, this is the a schematic showing the device structure of an organic heterojunction solar cell, in which you can uh, put two organic materials. So it can be sandwich one organic material or two different organic material in the form of donor acceptor pairs. And obviously the figure B is organic light emitting diode, is sector of organic light emitting diode. So obviously there is particular compulsion to orient the columnar materials. So if you want to fabricate the organic photovoltaic device or OLED device, you have to orient your disc-like molecule complete perpendicular to the substrate. And charge carrier mobility of this compound is very important in these devices, because the efficiency of these devices will be depend on the interfacial conditions and the charge carrier mobility of these molecules. So there is a question that is charge transport or charge carrier mobility important in these devices? Yes, it's very important. So here there are some of the paper, although I have not updated after 2023, but you can see some of these papers in which we have explored this domain. So here in our laboratory, we are particularly skilled to measure the charge carrier mobility in different organic semiconducting materials. So here basically we use certain techniques in which time of flight technique is very important. So here what happens, I will explain you that how we do how this technique works and how we do the with the measurement for that. So here we have a Nd:YAG laser of wavelength 355 nanometer and 532 nanometer. We need different absorption bandwidth of these laser lights, because this light should be absorbed by the material in order to release the exciton and electrons and holes. And obviously the pulse width and spot size you can change. So what happens, for example, if we take a discotic liquid crystal material which is semiconducting in nature, and you have filled this material in between your top electrode and bottom electrode, and you have to fix the thickness of this device, and obviously this thickness should not be less than 2 micron. So what happens when you irradiate this material with the laser light? This laser light is absorbed within the 10% width of the device by the material, and then what happens? This quantum phenomena, that one photon is absorbed by the molecule and it releases associated one exciton. So here you could see that when this photonic energy is absorbed by the material, it is generating the excitons. So what is excitons? Exciton is nothing but it's a quantum bound state of the electrons and holes. All of you might be knowing it from the quantum mechanics. And what is the important thing, that these excitons are not stable at room temperature. So what will happen? That these exciton will be dissociated in electron and hole, and due to thermal agitation they will be collected at the top electrode, because this light was absorbed within the 10% of the thickness of the device. And what will happen when you will apply a positive bias or negative bias at the top electrode? Then Coulombian forces will be effective here. So for example, if we have applied a positive bias here at the top electrode, and then due to Coulombian repulsion, this bias will repel holes, and these holes will be propagating towards the bottom electrode via interacting with these materials. And when you will apply the negative bias, then only negative element like electron will be propagating towards the bottom electrode. And then when electron or hole, they propagate from top electrode to bottom electrode, then you have to record their trajectory, photocurrent trajectory. So photocurrent trajectory can be of two type, one non-dispersive or dispersive. So when you have non-dispersive nature in the photocurrent curve, you can estimate the transit time by just taking an intersection between two tau. And when you have the dispersive curve, then you have to plot the curves in the log scale in order to estimate the transit time. And when you have the transit time, you can calculate the charge carrier mobility of electron and holes by using this formula, that is mu is equal to d square divided by v into tau. D is the thickness of the device and v is the applied voltage and tau is the transit time which we state. Okay. So this principle I have already explained you, that is the time of flight technique, which is a very nice technique to in order to measure the charge carrier mobility in organic devices. Second technique is space charge limited current method, in which you have to fabricate hole only device or electron only device in order to see the current voltage characteristic. So the current voltage characteristic will be having two parts, one region like ohmic region and one non-ohmic region. So in ohmic region, the current is directly proportional to the voltage, and in the non-ohmic region, the current will be proportional to the V square. And following the Moth-Gurney equation, you can estimate the charge carrier mobility. Third method to measure the charge carrier mobility is OFET. So you have to fabricate a organic field effect transistor devices in order to estimate the charge carrier mobility. Obviously, every technique has some pros and cons. So obviously, the time of flight technique is effective for electron and holes. You do not need two separate devices. And this technique is also very ionic sensitive. Ionic sensitive means if your material is not very pure, if it have ionic impurity, you can see the ionic impurity signal in your photocurrent curve. In this situation, you will have two transit, one corresponding to electronic charge transport, which will be very short, and ionic charge transport, ionic transition at the higher time scale. Obviously, SCLC is architectural dependent techniques, and in which like you need two devices to form, and sometimes the fabrication is quite complicated. And obviously, these devices, they often suffers with the trap and space charge region. So obviously, when your material or devices are full of traps, either it can be shallow traps or deep traps, then you have to do the correction in the Moth-Gurney equation, and without correction you will not get the equivalent the current. So OFET is very nice technique as well. However, it's very much dependent on the alignment. So higher the alignment, higher the mobility, and vice versa. So if you are not having very hands-on practice for the fabrication of OFET devices, you will not get very nice charge carrier mobility with the devices. So if you are interested in learning these techniques, you can go through these papers in which these techniques has been reported for the different organic semiconducting materials. So in fact, now we continued our research in exploring the different chemical system, and that was the organic materials. So this first system was developed by Professor Sandeep Kumar. So here you could see that this is the triphenylene core-based disc-like molecule. So this is called central core unit, that is made by triphenylene moiety. And here is the functional group. This is the alkyl chain. So R is the length of alkyl chain length. So here R is like CnH2n plus 1, and you can change n from 3 to 13. So what happens if you change the alkyl chain length? If you increase or decrease the alkyl chain length, you can prepare different homologs of these compounds. So here we have varied the alkyl chain length from n is equal to 4 to n is equal to 8. So obviously when you decrease the alkyl chain length, when you increase the alkyl chain length, when you will increase the alkyl chain length from n is equal to 4 to 8, the isotropic temperature got reduced. This is a typical behavior of structure property correlation. And what happens in these compounds, this particular compound is very interesting because here the alkyl chain length is shortest, and then it present very highly ordered phase, and it showed hexagonal plastic phase, and hexagonal plastic phase is the most ordered phase in the hexagonal family. So you could see here that these photocurrent curves, they changes depending on the length of alkyl chain. And here you could see when you go from HAT4 to HAT8, then obviously transit time shifts to the higher to this higher longer time, and then transit time will be longer, and then it will reduce the charge carrier mobility. So for the HAT4 material, we found the charge carrier mobility, especially for the holes, we found 10 to the power minus 2 centimeters square per volt per second. And this mobility, as you increase the alkyl chain length, the charge carrier mobility decreases. However, every homologs, they have shown that the charge carrier mobility is almost temperature independent. And till this report, this our field was having a stabilized fact that triphenylene based compound, they always show temperature and field independent charge carrier mobility. Okay, so who are the new in this field and they do not know the transport models in this field? So here I have a brief information for you that there are two type of transport phenomena in these materials. So first is called the hopping transport. So in hopping transport is basically hopping transport is associated with the disordered system. And in disordered system, so basically charge carriers are localized on the defect sites, and the lattice vibration is essential for carrier movement from one side to another. So charge basically jump from one side to another, and this is called the hopping process. Have you seen the frog, how frog walks during the rainy season? So it jump from one place to another. So this process is like the hopping process. And this hopping process, basically this process is thermally activated process, and then what will happen, the mobility will increase with increasing temperature. So this fact in these molecules, this fact was stabilized by Hana, a group of Hana from Japan. Until 2005, this was the fact. So obviously in the same year, another group from Busby from United Kingdom, they said not only the hopping transport, but band transport is also possible because these molecules can show some crystal-like properties as well. So basically the band transport is the characteristic of crystalline inorganic semiconducting material and some organic crystal materials. So what happened in the inorganic semiconductors? So atoms are basically covalently bonded. Okay, and in this situation, the delocalized charge carriers freely move along the band. And in crystalline material, the lattice vibration leads to the charge scattering. And in this band transport, basically mobility increases with the decrease in the temperature due to the lesser scattering, and they basically the mobility follow the power law. Okay, so why I told you this, because in our next investigation, a very interesting fact we came across. So because I saw we have already investigated this triphenylene based system in our last results. So idea was to induce the ambipolar charge carrier mobility in a system. So because this system only represented the whole mobility, so we have fused a phenazine unit into the triphenylene system in order to get the ambipolar charge carrier mobility. Okay, and here you could see that these materials was characterized by polarized optical microscopy, DSC, X-ray, and the time of flight techniques. So here you could see that very nice photocurrent curves. Okay, but here we found very interesting results. So here our whole mobility was in the order of 10 to the power 4 centimeter square per volt per second, and we observed temperature independent mobility in these compounds. And what happens, this whole mobility was increasing with increase in temperature. So as I told you before that in the triphenylene based system, the mobility was invariant with the temperature. This was the stabilized fact until 2005. And one another group from Japan, led by Takashi Kato, they showed temperature dependent mobility in oligothiophene systems. However, their mobility was increasing almost linearly with the increase in temperature, and he just said that viscosity is the factor for which this mobility is changing. Okay, and our system was completely surprising. So we repeated this experiment several times, and after that we went into literature. Okay, so if you have seen the mobility behavior of a single crystalline material, that is governed by the power law. Okay, but our system is not single crystalline system, not crystal like system. This is a disordered system. So when we have fitted the data, it was following the inverse power law. So inverse power law was associated with the centrosymmetry breaking. So later on, I will explain you what is the centrosymmetry in that. So basically, this temperature dependent mobility was associated with the centrosymmetry breaking of the compound. Okay. So centrosymmetry is that we continued our research on the another systems also on another compound which was developed by Dr. Monica Gupta. She started her career at IIT Ropar, and now she is at IIT Jodhpur. She very recently joined IIT Jodhpur. So if you see here this molecule, that is a triphenylene molecule. So this is a symmetrical molecule and its shape is disc-like. So in disc-like, the center of mass lies always at the center here. So this molecule exhibits centrosymmetry things. So what happens if you fuse this material with a wedge-shaped moiety, then what will happen? The centrosymmetry will be shifted here. So this means this will be a breaking of centrosymmetry. So when centrosymmetry is broken, what happened? You could see here the mobility behavior. If you see, we observed a very nice photo current curves here, and here the mobility was in the order of 10 to the power minus 3. However, we observed the temperature dependent mobility. So this was the proof of another proof of concept that what we did a hypothesis in our last investigation that was proven for this compound, and later on we communicated this in chemical communications. And obviously, this charge transport phenomena was driven by the thermally activated charge carriers. And these thermally activated charge carriers, they were originated from positional disorder, because as I told you that these systems, they make these are the disordered system. They are not ordered systems like crystalline solids. And obviously in the liquid crystalline phase, because as I told that they will also possess some viscosity and surface tension, so factor of viscosity will also be influence you, but it depends. Okay, and later on, we again continued our investigation on this aspect. So one another compound was created by our collaborator. I would like to tell you that I am a physicist. I am not an organic chemist. So that's why I am always dependent on my chemist collaborator to provide us some good materials. So obviously later on the Santanu Pal group has created one moiety that is called this is the triphenylene based system, and they fuse the triphenylene based system with the pentaalkyl benzene diodes. So this is pentaalkyl benzene diodes. So basically this material itself represents centrosymmetry, and this material also represents centrosymmetry. So there are two moieties which have centrosymmetry. So when you fuse two symmetrical system exhibiting centrosymmetry, so centrosymmetry will remain at the same place, it will not be disturbed. Okay, so later on we investigated the charge transport phenomena is these compounds. So you could see here, obviously due to the bulky nature of the molecule, the photocurrent curve was very noisy. However, because centrosymmetry was not broken, we observed the temperature invariant charge carrier mobility in the order of 10 to the power minus 3. This compound was really very interesting because we observed MB polar charge carrier mobility corresponding to electron and hole. Obviously, the electron charge carrier mobility was little higher in magnitude as compared to the holes. And why this compound was very interesting, because this compound was later used to fabricate the blue LED. And this was the first report for the fabrication of blue LED using discotic material. So obviously here they are the structure of the LED. Here is the characterization of the LED. You could see here. So what was the thing that obviously it was done with our collaboration. And first time this report represented that this type of organic semiconducting material can be used to fabricate the blue LED. However, the external quantum efficiency was not very high, it was just 2.1%, but it was also very nice, and the reports went to Journal of Materials Chemistry C. Now I would like to extend the use of these materials into the other organic photovoltaic devices. So here you could see that there can be different architectures of the organic photovoltaic devices, in which that you can sandwich a single layer of organic materials in between the cathode and anode. While to increase the efficiency, you can separate the acceptor and donor layers, and you can introduce the electron transport layer, hole transport layer, and so on, or you can mix the donor acceptor things. Obviously, there are so many architectures associated with the photovoltaic devices. I'm not going to tell all the things, but if you are interested, you can go to my this book chapter in which we have covered all these topics, that metal oxides in organic solar cells, that was published by Elsevier in 2023. So what are the main challenges is these photovoltaic devices? So as you know that basically all the photovoltaic devices, they are made with the PN semiconductors, P-type and N-type semiconductors, and then you have to make a PN junction in order to get the external voltage or current. So what happened when you make a PN junction device? Then electron basically propagate in the external circuit in order to produce the external voltage or current. But sometime happens, depending on the interfacial condition, depletion layer and so on, these electrons, they do not propagate in the external circuit, they come back and they rebind with the holes. This process is known as charge recombination. So when electron and holes, they recombine each other, then pair inhalation phenomena takes place, and they inhalate each other, and they produce the equivalent heat. And this degrade the device quality and efficiency. And second the problem, that because these semiconducting material P-type or N-type, they have very high dielectric constant. So very high dielectric constant produce additional interfacial losses in terms of, maybe it can be the heating effect or Joule heating effect, and so on and so on. So now we thought that why not to use these columnar materials at the interface, because these materials, they compel charge carrier to move along the one dimensional direction. So before directly going to the fabrication of devices, we thought to do a proof of concept. So we contacted our colleague Professor A.S. Achal Kumar at IIT Guwahati to, to make a particular columnar material that is shown here, that is called, short name is PQ10, and we characterize it. And then we took one reference parental device that was reported by the group of CRISP in ACS Applied Energy Materials. And here, this is the structure of a quantum dot based solar cell device, in which he used the ZNO, INP and MOO3. So MOO3 is used as whole transport layer materials. So CRISP and his colleagues, they showed that this device has showed the short circuit current density around 8.3 milliampere per centimeter square, and the PCE for this solar cell device was 0.64%. So then, to prove our concept, we replaced this MOO3 layer by the PQ10 material, and we remained the other structure same. And then the JSC was found to be 9.3 MA per centimeter square, and PCE was increased to be 0.68%. So this was the first proof of concept that these columnar material can be used at STL, and this can also be used at the interface in order to improve the efficiency of the material. Okay, so here under our joint project with the Notapan and Pongthep from Kasetart University, Thailand, we fabricated the three devices, one with the perovskite material under this, and then we inserted our HAT4 material at two interfaces, one in between the perovskite material and PSS, and second at the PSS and ITO substrate. So what happens, basically charge recombination will take place at the PSS and perovskite material interface, and second, sometime in these devices, what happens that charge carriers accumulate at the ITO substrate, and then this phenomena accumulation of these charge carriers, they results in the changes surface electrode polarization, and then generation of this surface electrode polarization, they diminish the efficiency of these devices. So that's why we thought to insert our this material at the two places. Okay, so obviously we were not the first to introduce this concept. It was the first group of Zheng from China. They introduced this approach. However, they found the PCE of the device only 3%. And later on, this approach was continued by the group of Wang. They found the PCE of 14%. However, they used a fullerene-based system. And due to the new regulation of the European Union, we do not want to use the fullerene system because it's not environmental friendly. So obviously, our results are recently appeared in ACS Applied Electronic Materials. So if you are interested in this field, you can go to this paper. So obviously, we fabricated the 10 devices and the device, and we investigated the all parameters like PCE, JSC, VOC, fill factor, and so on. And here is the conclusion of these devices. So the parent device without any columnar interfacial layer, the PCE was around 10.5%, and when we introduced this columnar material at the interface, the PCE increased and found to be 12.2%. So obviously that we can say that control over interfacial charge recombination via one-dimensional charge migration through columnar material is responsible for this increased PCE. And obviously that the presence of one-dimensional molecules and charge transportation, which is restricted to one dimension, it improved the molecular ordering at the interface. Okay, one of the problem with these molecules that they are non-polar, their dipolar moment is around 1 to 2 dBi. So they do not show any influence with the field. So one another system was developed by our collaborator Matthias Lehmann in Germany, and his PhD student got 1 month fellowship to work in my laboratory to over that. So they developed a subthylocyanine based system, and this molecule can be oriented using the external applied field. So what happened when you applied the field? We investigated this charge carrier mobility, and we investigated the charge transport phenomena in that. So okay, obviously because this molecule was very heavy, so we got the dispersive photocurrent curve. So here you could see the dispersive photocurrent curve. So obviously what happens, basically you could see the different regions here. So the first region here, when you irradiate the material with the laser light, so charge generation takes place, and after that charge propagate from a top electrode to bottom electrode. So because this part should be the constant. So if the charges have the constant velocity, you will get the plateau. But if it is not plateau, if it is dispersive, then this means there is no constant velocity of the charge carriers. And then the charges will arrive at the electrode. So as here I have shown that these photocurrent curves are dispersive, then there are certain region behind that, and due to the bulk nature, maybe it is impurity or thermal instability. And later on, like we align these materials, so obviously when the material is partially aligned or well aligned, then you will get the better mobility. So for example, here due to the higher alignment, the mobility was in the order of 10 to the power minus 3, and in this material showed ambipolar mobility. And when it is partially aligned, then obviously the charge carrying mobility is lesser than the ordered method. And later on, we also fabricated the different devices using these material. And obviously, the concept that when we use our these columnar materials at the interface of the perovskite material in P.PSS, this showed the best efficiency around 11%. So these are the devices, 5 devices, whatever we fabricated. And this was the IV curves of the best device, in which we found the PCE around 12%. Okay, so continue to this approach. We utilized this approach to the LED structure. So basically, if you see here, this is the structure of the LED device, in which like you have an emissive layer in between your cathode and anode, and ETL and HTL, and obviously you will be having different RBG filters and so on. And one important technological thing, that the thickness of this device should be less than 500 nanometer. And why the LED structures are very important? Because in 2014, a Nobel Prize was awarded for that. Okay, and here you could see here, this is the external quantum efficiency of the LED, which is the product of the charge balancing factor, photoluminescence quantum yield, and light coupling efficiency. So basically, these are the some problems of the LED devices, that hole injection and transportation. In out efficiency is maximum 30% reported at the laboratory level. However, commercial is around 26%. And when you want more luminescence from the LED devices, you have to apply more voltage. And when you apply the more voltage, then what happens, that large drooping effect takes place, and auger effect and large leakage current are the associated problems with that. And obviously you can cope this problem. So here we have done this with a joint project with the Hong Kong University of Science and Technology. So obviously TFB is the polymeric material which is used as a whole transport layer material in the LED devices, which you use commercially or at your home. And one basic problem with these materials is their limited hole mobility, that is 2 into 10 to the power minus 3 centimeter per volt per second. So we used the first our material, pristine material, as a whole transport layer material, but unfortunately it didn't work. And then we thought to mix the HAT4 material with the TFB. So when we mixed around 20% of the HAT4 with the TFB, and we measured the current density and so on and so on, and we found that current density has been increased, because this is HAT4 is the photosensitive material. It generate the photo carriers. Then this means that increase in charge carrier density is associated with additional charge injection in the device, and that's why the charge current density of the LED device is increased. So we recently published this paper in this journal. So the conclusion of the part 2 is that you can use these organic semiconducting materials in all type of organic electronic devices and optoelectronic devices, depending on their charge carrier mobility. And these are the some technological challenges in order to increase the LED and LED performance at the present technology. Okay, so I leave this message to the chemist and physicist. If you are working and if you are interested in working in the LED field, you can take these points as a challenge in order to improve the present technology. So okay, I have sort of time, so but I will quickly finish my third part. So third part is associated with the ferroelectric pneumatics. As I told that in the current technology, we use solid ferroelectrics, which have the microcoulomb per centimeter square spontaneous polarization. So in fact, the soft ferroelectrics, they have their spontaneous polarization in the order of nanocoulomb per centimeter square. But however, in 2019 and 2022, a new phase has been developed that is called ferroelectric pneumatic. And in that ferroelectric pneumatic, the spontaneous polarization value is found in the order of microcoulomb per centimeter square, that is equivalent to the solid ferroelectrics. So basically, these are the conventional pneumatic phases, as I told you in the introduction section. And these conventional pneumatic materials, they have been used in electro-optics and display devices. And later on to now, the ferroelectric pneumatic phase has been developed. However, the hypothesis of ferroelectric pneumatic was done 100 years back in around 1910 by Debye and Born, and now it is realized in 2019. Okay, so first system that represents this ferroelectric pneumatic was developed by Richard Mendel, University of Leeds. So what happens in the pneumatic phase? Basically, the molecular orientation is pointed either upward and downward. So N plus and N minus are the same. So overall, this phase is non-polar because dipoles cancel to each other. And what happens if the symmetry is broken? Then when symmetry is broken, then all dipolar orientation will be in a single direction. And then in this situation, L will not equal to -1. And then this makes this phase polar. And these were the first reports by the Mendel and one group from Nishikawa from Japan. But in 2017, they didn't coin this phase as a ferroelectric pneumatic. This was a polar band phase, but in 2022, first time the name was given to ferroelectric pneumatics. And their high polarization is around 4.5 4.4 for the DIO and 6 microcoulomb per centimeter square for this material, and dielectric constant is very high. So as this is the molecular structure of this RM734, and you could see here that the spontaneous polarization is around 6 microcoulomb per centimeter square, and this polarization changes when this material changes from ferroelectric pneumatic to pneumatic transition. Okay, so here we have developed some photopyroelectric techniques. So basically, we wanted to make it as energy generators, pyroelectric energy generators. So this is the principle. So when transient heat flux is incident on these materials, then what will happen, depending on the polarization and change in temperature, it will additionally generate the electricity here. So IP is basically PA dt by dt. So this is the like change in temperature as a function of time, surface area, and the polarization with that. So here we have used this photopyroelectric technique, in which we have the pyroelectric sensor material, and then we irradiate here with the laser light, and we analyze the change in 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 signal, current signal, as a function of change in temperature. So obviously we have certain advantage and disadvantage of this technique. It is very sensitive, but however it's a good resolution in the order of millikelvin. A low quantity of material is needed, and this is the one-dimensional model. However, two-dimensional model is also possible. The weakness is like single crystal, and this because we use these pyroelectric sensors, so it is very brittle and very costly, and so on. So with the RM73, we have measured the thermal behavior. So you could see here, here is the phase is pneumatic, and this is the ferroelectric pneumatic phase. So you could see here there is the signal strength is weak. So here we estimate, we do a lot of mathematical treatment of the data, and we found that first of all we estimate the thermal parameter called effusivity and diffusivity, and then we calculate the thermal conductivity or that. So this is the thermal effusivity with the temperature study. So here you could see that in the pneumatic phase the signal is high, and then when it comes to the ferroelectric pneumatic phase it's less. So when you can calculate this, numerical solution is required, and we do a lot of mathematical treatment for that. And then what we found, that the thermal conductivity of this compound is very low. However, it is electrically conducting. So however, this study didn't complete yet, and we are still continuing the study, but this particular material is of interest because this material is thermally insulating. However, it is electrically conducting. So this material can be very nice for future quantum technology, especially the material by which we are fabricating the RAM and the computings. So here are the conclusion of my third part, which is the last part. So exhibiting large dielectric constant in the order of 10 to the 4 and micron order polarization, it can be the future of liquid crystals, and also for the organic semiconducting material. Thermal conductivity is lower in the NF phase with respect to pneumatic phase, and such high value of polarization is equivalent to the solid state ferroelectrics. And now what will happen, that because it is electrically conducting and thermally insulating, therefore it can be used in the next generation quantum technologies. So here is a small advertisement that if you have, I am just reading this journal like Willy Chemistry and Asian Journal. So if you are interested in submitting any of your work within the scope of this, you can submit. And one another we are just editing in the Springer, that is a polymer journal, Discover Polymer Journal. So obviously you are more than welcome if you are interested in submitting your results. So thanks to all my collaborators around the globe, because what result I have presented is not possible without their cooperation, and obviously plenty of collaborators from different parts of the European Union and other part of the globe, and obviously all our Indian partner with whom I have active collaborations. So alongside the collaborators, I would also like to thank all my students, the Vanishri who is doing postdoc with me, the Asmita and Vinso who recently finished their thesis, and my third student Mamadu who will be finishing his thesis in December 2025. So obviously not only my PhD student, I can host some of the PhD student for the certain time. So I hosted the 3 PhD student from Tunisia, Thailand, and Canada, and obviously, like if you are interested in our activity, and you can also apply if you are looking for the short-term mobilities and to work in my laboratory, you are more than welcome. And we also host some master internship for maximum 6-month thesis work. So you can have different fellowship opportunities as well, or the financement from our laboratory. You are more than welcome to contact if you are interested in our research activities. So obviously here I would like to tell you some opportunities So if you are very like the France government has initiated the France Excellence the program that is called IFIL Excellence Program. So you or your students who are like a PhD student or master student and they are like topper in that, so they can apply for this scholarship. And for the PhD student they can apply for the Raman Charpak Fellowship. And all the faculty members they can apply for short-term mobility via French embassy, and that is called the scientific high-level visiting fellowship is up to the 2 weeks. And if you are looking for the postdoctoral position, then this is the initiation of make our planet great again. So still the call is open. If you are interested, you can apply under these schemes. So at last but not least, I would like to thank all my funding agencies for providing me the funding and industrial partner, the Merck, with which I have like a material evaluation contract on that. And at last, I would like to thank you all for your kind presence, and I would love to answer if you have any question. Thank you so much.
Thank you very much, sir. Indeed, a very, very nice presentation. And we could able to know the various aspects of organic semiconductor. And here we have a question, sir.
Yeah, sure. And
What
I hope
makes...
I was on time. I didn't take a long time. Yeah.
No, no, sir, not at all. Perfect, sir, perfect.
Uh,
Rajesh Singh, sir, can you please can you ask the question? So the question is, what makes columnar materials suitable for roles like HTL and ETL in optoelectronic devices?
Okay, so basically, as I told you that these columnar material, they have a pi conjugated core and aliphatic chain around it and some functional group. So depending on the electron deficient nature or electron rich nature, you can use these material as HTL or ETL.
Okay.
Yeah, so if the core is electron rich, then you can use as STL. If is it electron deficient, then you can use as ETL. So it is only the chemical composition you have to change. So you have to demand, if you are chemist, you can design your molecule, or if you are physicist, then you have to demand your chemist to design some molecules with electron rich or electron deficient core. That is how you can change its a position on the device that you can use as ETL or STL.
So do organic semiconductors have any role to play in memory devices?
Yes, definitely. Definitely some memory devices are being reported using these organic semiconducting material. However, the problem is still with the losses, because when you have like, because for the memory you have to do the two cycles, like when it should be like, for example, polarization based memory, then what will happen that the polarization will change from positive field to negative field, and then what happens, you will have the hysteresis. So with this material, for now, there is high degree of hysteresis in that. So hysteresis represent a type of losses. So some, you can fabricate the memory devices, but some information is being lost during the analysis. So obviously, I think it's now it's a challenge for the chemist to make the efficient material that can be used in high quality memory devices.
True, sir. Thank you, sir. Thank you very much. Thank you.
Thank you. Is
Sir,
there
thank you
any
so much.
other question? So I can, yeah, maybe I will. Okay. Yeah, so if there is any other question, I can answer. And anyway, if you have any other question for the later on, I have shown my email on the first page. You can write to me, and definitely I will answer.
With your permission, I will post your email ID to them, sir, in our
Yeah, yeah.
WhatsApp channel.
Email ID will be better. Yeah. So
Yes, email
that
ID I will post, sir, definitely.
yeah, yeah. That will be very fine for
Sure, sir,
everyone
sure.
to yeah.
Sure,
So
sir,
for
sure.
example, maybe for the next 2 weeks, maybe I will not be able to respond because from tomorrow I am going to travel to India. But from 1st of December, I will be available to respond immediately. So maybe if you write me an email, you will get a auto response till 1st of December that I am out of office. But obviously, I will try to answer once I will get the internet and so on. Yeah.
Sure, sir, sure. If you are coming to India, then you visit to our place also, sir. One
Yeah.
or two
So
days. It is
yes.
filled with rich forest, sir. We are
Yeah.
surrounded by forest,
Yeah.
and
So th
it
thank you so much for the invitation. So for this time, please excuse me. It's a little difficult because 2 weeks program is I am going to BITS Pilani and I have a function at home. So, but definitely next year I will be visiting India again for longer time in between February and April. Then obviously I will contact you and I will visit the places. Yeah.
please, sir, please.
Yeah. Yeah.
Thank you
Yeah.
so much, sir.
Yeah. Thank you
Thank
so
you.
much. Thank you so much.
Yes, sir. Sir, I have taken the photograph. Sir, if
Hello.
participants do not have any questions, do you?
Yeah, hello.
Yes, sir. Go ahead, sir.
Sir, I am from BITS Pilani.
Okay. Yeah.
So, where you are attending this session, sir? So, I am here. I am here. I am a PhD scholar in BITS Pilani.
Okay.
So,
So in
where are
fact,
you?
there is a conference in BITS Pilani from 20 to 22nd November, organized by
Yes, sir.
Head
Yes,
of
sir. Yes, sir.
Department Physics, Professor
Yes, sir. Yes, sir.
Rajkumar
Yes, sir.
Gupta and Professor Manjula Devi. So I will
Yes,
be
sir. Yes, sir.
visiting your campus.
Manjula ma'am is the head of the Department of Physics. Physics, sir.
Yeah, yeah. So in fact, we have signed a MOU between my university, my French university, and BITS Pilani. So there will be a lot of
Okay, sir.
joint activities there. So if you are there, so obviously we can meet there. Yeah,
Definitely, sir. Definitely. It is
yeah,
my pleasure to meet you, sir.
yeah, yeah.
Thank you so
Thank you.
much, sir.
See you
Thank you
there.
so
Yeah,
much.
yeah.
Yeah, definitely, sir. So I will be there. Any, I will share with you my contact number.
Okay,
You need
perfect.
any help, any regarding that? I am my pleasure to meet you, and I'm always available for you, sir. Thank you so much for
Okay, thank you
visiting
so
us.
much. So let's meet during the I will be reaching by 19th night. So but I will
Okay,
be
sir.
available there from 20 to 22nd. So definitely it will be my pleasure as well to meet the young minds. Yeah. So see you there,
Thank you
Rajesh.
so much.
Thank you, Rajesh.
I will share my contact number with sir, and they will
Okay,
transfer
perfect.
to you. So you have
Perfect.
any
Okay.
contact number, sir? I will text you on that number.
Yeah, yeah, yeah. So just text me and I will text you back. Yeah.
Okay, 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 sir. Thank you so much,
Okay.
sir.
Perfect.
Okay, sir.
Okay, thank you, Samir sir. So
Yes,
if there is no question, so
yes, sir.
maybe give me permission to leave the meeting.
Sir,
Yeah.
let me propose vote of thanks on behalf of
Okay.
all my dear participants of this FDP and on behalf of my institution and on behalf of my beloved principal, Dr. V.A. Kulkarni sir, and all these organizing committee members. I wholeheartedly thank you for supporting this our FDP, and I hope that this interaction, this cooperation and collaboration will continue in future also. We expect you and we hope you will say definitely yes to all our future endeavors, sir.
Yeah,
And
thank you so much, Samir sir. Thank you so much,
yes,
and I hope that my research activities inspire these young minds. And obviously, I am always ready for any joint research activities and anything. So, if anyone has any opportunity to come abroad to work with me, I am always ready. And please do not hesitate to write me. Yeah. So and to everyone, my best wishes. And yeah.
Thank you,
So
sir. Thank you.
hope to see you. Yeah.
Bye, sir. Bye, sir. Take care.
Okay.
Thank
Bye bye,
you.
sir.
Thank you, sir. Bye, sir. Bye. Stop recording. End the meeting.